Hello there, and welcome to the Cosmographer. Right now, the honest scientific evidence that we are not alone in the universe is stronger than it has ever been in all of human history, and almost none of it looks the way the films promised. There are no saucers on the lawn. There are 300 million worlds in this galaxy alone that could hold liquid water. There is a moon of Saturn spraying the ingredients of life into open space. There is a signal that arrived once from the direction of Sagittarius, at exactly the frequency a stranger would choose, and then never returned. There is an object that fell in from another star, accelerated on its way out, and left before we could photograph it. And there are 3 videos that the Pentagon spent years refusing to explain, and then confirmed were real. Tonight, across 3 unhurried hours, we count down the 10 most obvious signs that we are not the only living things in the universe, ranked by how directly each one points home. And the sign at number 1 is not out among the stars at all. It is the one you have already seen. Get comfortable and settle in. If you enjoy falling asleep to the real evidence told honestly, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this countdown, the most obvious sign that we are not alone will turn out to be far closer than any star on this list. Let's begin at number 10. Number 10. A sky full of Earths. This is a list of evidence. Not rumors, not blurry photographs passed around without a source, but 10 signs, each with names attached, dates attached, and instruments attached, that together make the case that we are probably not the only living things in the universe. Some of these signs are statistical. Some are chemical. Some are signals that arrived once and never returned. One of them sailed through our solar system and left before we could photograph it properly. And the sign at number 1 is not out among the stars at all. It has been sitting in plain sight for longer than our species has existed, and by the end of tonight, you will see it for what it is. One rule governs this entire countdown, and it is worth stating before we begin. Every claim on this list will carry its honest label. When something is confirmed, we will say, confirmed. When something is contested, we will say, contested. When an idea is pure speculation, even speculation published by respected scientists, we will call it speculation. The strange thing about this subject is that the honest version is more remarkable than the exaggerated one. The universe has been generous with clues. It has simply been careful with proof. We begin with the sign that changed the question itself. Within living memory, it was scientifically respectable to wonder whether planets were rare. Not life, planets. As recently as the early 1990s, not a single world had been confirmed in orbit around another star like our Sun. Astronomers assumed they were out there, but assumption is not evidence, and the number on the board was 0. Every argument about alien life rested on a guess about how many worlds existed for life to live on. The guess could have gone either way. Perhaps planet formation was a fluke, a lucky accident of our particular cloud of dust. Perhaps the Sun's family of 8 was the only family in the neighborhood. Then, in October of 1995, 2 Swiss astronomers ended the question. Michel Mayor and Didier Queloz, observing from the Haute-Provence Observatory in southern France, announced that a star called 51 Pegasi, about 50 light-years away, was wobbling. It wobbled in a small, regular rhythm, the signature of an unseen companion tugging it back and forth. The companion was a planet, at least half the mass of Jupiter, and it was racing around its star once every 4 days. For comparison, Mercury, the fastest planet we have, takes 88 days. Nothing in our solar system prepared anyone for a giant planet skimming so close to its sun that its year fit inside a working week. The discovery was so unexpected that some astronomers initially doubted it, and so important that, 24 years later, it earned Mayer and Queloz the Nobel Prize in Physics. 51 Pegasi b was the crack in the dam. Once astronomers knew what a planet's signature looked like, they began finding them everywhere. And in March of 2009, the search became industrial. NASA launched a space telescope named Kepler, after the astronomer who first worked out the mathematics of orbits, and pointed it at a single patch of sky on the border of the constellations Cygnus and Lyra. Kepler did one thing, and it did it with superhuman patience. It stared, without blinking, at roughly 150,000 stars at once, for years, watching for the tiny dip in brightness that happens when a planet crosses the face of its star. The dip is almost comically small. When an Earth-sized planet transits a Sun-like star, the star dims by about 1 part in 10,000. Astronomers compare it to watching a flea crawl across a car headlight from miles away and noticing the light flicker. Kepler noticed. By the end of its mission, it had confirmed more than 2,600 planets in that one patch of sky, and its successors have pushed the total count of confirmed exoplanets to roughly 6,000, with thousands of candidates still waiting in line. 6,000 confirmed worlds, in one generation, after all of previous human history produced none. And because Kepler watched a known number of stars, its catalogue could do something no discovery before it could. It could turn the question of other Earths into arithmetic. The arithmetic says this: roughly 1 in 5 stars like the Sun appears to host a planet close to Earth's size, orbiting in the habitable zone, the band of distance where a world receives enough light for liquid water, but not so much that the water boils away. Extend that fraction across the galaxy, and the numbers stop behaving like astronomy and start behaving like a census. A widely cited estimate built on Kepler's data puts the count of potentially habitable rocky worlds in the Milky Way at around 300 million. Some estimates run higher, into the billions. 300 million is the cautious figure, and it is worth pausing on. If you visited one habitable world every single day, it would take you more than 800,000 years to see them all, and that is one galaxy out of trillions. Within that census, one world became famous, and it deserves its fame with a few honest footnotes. In July of 2015, the Kepler team announced Kepler 452b, quickly nicknamed Earth's older cousin. It sits about 1,400 light-years away. It orbits a star remarkably like our Sun, at nearly the same distance we do, taking 385 days to complete its year, 20 days longer than ours. It is about 60% wider than Earth, which makes it what astronomers call a super-Earth, a class of planet our solar system happens to lack. If it is rocky, its gravity would be stronger than ours, its atmosphere likely thicker, its mountains and weather built on a heavier scale. The footnotes matter, so here they are. Kepler 452b's mass has never been measured, which means nobody knows whether it is truly a rocky world or a small ball of gas. Cousin describes its circumstances, not its confirmed nature. But one measured fact about the system is the reason it belongs on this list. Its star is about 1.5 billion years older than the Sun. Whatever that world is, it has been sitting in its star's habitable zone with a head start of 1.5 billion years. On Earth, 1.5 billion years is roughly the distance from the first single cells to creatures with bodies. If anything ever began on that world, it has had time we can barely conceive of. And if intelligence ever arose there, it would look back on our entire recorded history the way we look at the last few seconds before midnight. The census also turned up worlds nobody asked for, and they widened the picture in ways worth hearing. The very first planets ever confirmed beyond our solar system, in 1992, were not around a Sun-like star at all. They orbit a pulsar, the spinning corpse of an exploded star, a place bathed in radiation where no textbook said planets could exist. Yet there they are. Other planets circle two suns at once, like Kepler 16b, where a visitor would watch a double sunset every evening. And some planets belong to no star at all. Surveys that watch for the gravity of unseen bodies bending starlight suggest the galaxy holds rogue planets in enormous numbers, possibly trillions, wandering the dark between the stars. Planets, it turns out, are not delicate or rare. They form nearly everywhere, survive nearly everything, and outnumber the stars themselves. This is where a blackboard in West Virginia enters the story. In 1961, a young radio astronomer named Frank Drake convened the first serious scientific meeting on the search for extraterrestrial intelligence at the Green Bank Observatory. To organize the discussion, he wrote an equation on the blackboard, a chain of factors that together estimate how many communicating civilizations the galaxy might hold. How many stars form each year? What fraction have planets? How many of those planets could support life? Then the biological terms, the fraction where life actually begins, where intelligence arises, where technology follows. In 1961, every single term was a guess. Here is what the exoplanet revolution actually accomplished, and it is the honest payoff of this first item. The first several terms of Drake's equation are no longer guesses. They are measurements. Star formation, measured. The fraction of stars with planets, measured, and it is essentially all of them. The number of habitable zone worlds, estimated from real survey data, and the answer is hundreds of millions in this galaxy alone. Every term science has managed to measure has come back generous. The universe, wherever we have been able to check its arithmetic, has answered on the side of abundance. The remaining terms, the ones about life itself, are still blank. But the stage, which was the great unknown for all of human history, is now confirmed, and the stage is enormous. So consider what happened in the space of a single human generation. A question that had stood unanswered since the first person looked up, whether other worlds exist at all, was asked, answered, and buried under 6,000 confirmations. Nearly every star you can see tonight, if you step outside and look up, is now understood to host at least one planet on average. The sky you have looked at your whole life did not change. What changed is that we now know it is not scenery. It is an ocean of places. The question is no longer whether there are other worlds. The question is, which of them, if any, is looking back? Keep one image from this item, because this list will return to it at the very end. When astronomers hunt for a living world among those 300 million candidates, they carry a short checklist. Water in its liquid form. Gases in the air that should not last, unless something keeps making them. And, for the boldest hope, a signal with order in it. Water, restless chemistry, ordered signal. A checklist for a living world. Hold on to it. Because before this night is over, that checklist is going to point somewhere you do not expect. It is worth dwelling on how thoroughly the transit method has reshaped the picture, because the technique itself is a small marvel of patience. A planet does not announce itself. It betrays itself only if its orbit happens to be edge-on from our point of view, so that once each year, by its own calendar, it slides directly between us and its star. Most planetary systems are tilted the wrong way and stay invisible to this method entirely, which means that for every planet Kepler saw, geometry hid a dozen or more it could not. So when the survey found that transiting planets were common, the honest correction was to multiply upward, not down. The worlds Kepler counted were only the fraction that happened to line up. Behind each of them stood a crowd of siblings orbiting at angles that never crossed the star's face for us. The 300 million figure is not the optimistic ceiling. It is closer to the conservative floor, built from the minority of systems kind enough to show themselves. There is a second technique worth naming, because it is the one that started everything and it works in the opposite way. When a planet orbits a star, the star does not sit perfectly still. The two bodies circle a shared center of mass, and the star traces a small answering wobble, swinging toward us and away, over and over. As it swings toward us, its light shifts imperceptibly bluer, and as it recedes, imperceptibly redder, the same effect that raises and lowers the pitch of a passing siren, applied to starlight. This is the radial velocity method, and it is what Mayer and Queloz used on 51 Pegasi in 1995. It measures a star's motion to within a few meters per second, walking speed, across light years of empty space. Between the wobble method and the transit method, astronomers can often learn both a planet's size and its mass, and from those two numbers, its density, and from its density, whether it is a ball of rock, a world of water, or a puff of gas. We are not merely counting distant worlds, we are weighing them. Consider what that weighing has revealed about the sheer variety out there, because variety is its own argument. Before 1995, we had one planetary system to reason from, our own, tidy and graded, small rocky worlds close in, giants far out. The galaxy has since made a mockery of that tidiness. There are hot Jupiters skimming their stars in days. There are the super-Earths and mini-Neptunes, the single most common type of planet in the galaxy, of which our solar system contains not one example, so that the most abundant kind of world is one we had never seen until we looked outward. There are systems packed tighter than ours, water worlds, lava worlds, worlds where it likely rains rock or glass. Nature, given the chance, does not build one kind of planet. It builds every kind, in enormous numbers, around nearly every star. And in that riot of variety, the Earth-sized rocky world in the temperate zone is not an exotic prize. It is one common design among many, stamped out again and again across the galaxy. There is a temptation, hearing numbers this large, to let them wash over you as mere bigness, so it is worth grounding one of them in something you can picture. Take the low estimate, 300 million potentially habitable worlds in this one galaxy. Picture them as a library. One book per world, each book the biography of a planet that could, in principle, hold life. 300 million books is larger than the collection of any library that has ever existed on Earth. And we have read, so far, the first few sentences of a mere handful of them, the nearest and brightest, the ones easiest to reach with our instruments. The rest sit on the shelves unopened, each one a temperate, rocky world with liquid water somewhere in its story, each one a place where the same chemistry that woke on Earth had a genuine chance to stir. That library is one galaxy's worth, and there are something like 2 trillion galaxies within our view. The mind cannot truly hold a number like that. It can only register the direction it points, which is away, decisively, from the idea that our world is the only one of its kind. But statistics, however enormous, only tell us where to look. They are a map of possibility, not a destination. The next sign on our list is different. It is a specific address, 40 light-years from where you are lying right now, where a small, patient telescope found not one promising world, but 7 of them, all at once. Number 9. 7 worlds around one small star. The story of this address begins with a telescope that most observatories would consider modest. In the Atacama Desert of Chile, a Belgian team operated an instrument called TRAPPIST, a robotic telescope with a mirror just 60 centimeters across, about the size of a serving platter. Its full name is the Transiting Planets and Planetesimals Small Telescope, though its acronym was also a wink at the famous Trappist monasteries of Belgium. While the giant observatories of the world chased distant galaxies, TRAPPIST watched something almost everyone else ignored. It watched the smallest, coolest, faintest class of stars in the galaxy, the ultra-cool red dwarfs, on the theory that finding planets around small stars is easier, because a small planet blocks a larger fraction of a small star's light. The theory paid off in a way nobody quite dared to predict. In 2016, the team, led by astronomer Michael Guillon of the University of Liège, announced that one of their target stars, 40 light-years away in the constellation Aquarius, was being crossed by planets. 3 of them, each roughly the size of Earth. That alone would have made the star famous. But when the team looked closer, the transits refused to add up cleanly. There were too many dips, in too many rhythms. Something more was hiding in the data. So NASA aimed a far more powerful instrument at the little star. The Spitzer Space Telescope, an infrared observatory floating in deep space, locked onto the system and stared for 500 hours without interruption, nearly 3 weeks of continuous watching. Spitzer untangled the overlapping shadows one by one. And on February 22, 2017, NASA called a press conference to announce the final count. 7 planets. 7 rocky, roughly Earth-sized planets, all orbiting a single star, the largest family of Earth-sized worlds ever discovered around one sun. The star was renamed TRAPPIST-1, and overnight it became the most famous planetary system in the galaxy after our own. It is worth slowing down to appreciate how strange and how promising this little system is, because every detail sounds invented. The star itself is barely larger than the planet Jupiter, though far heavier, holding about 8 to 9% of the Sun's mass. It is an ember, glowing mostly in infrared light, 2,000 times fainter than the Sun. It is also ancient, around 7.5 billion years old, some 2 billion years older than our solar system, and it is a miser with its fuel. A star that small will keep shining, essentially unchanged, for trillions of years. Every sun like ours will have died and gone dark while TRAPPIST-1 is still quietly warming its family. If life needs time, red dwarfs offer more time than the universe has yet lived. The 7 planets huddle close to their faint star, so close that the entire system would fit comfortably inside the orbit of Mercury. The innermost world completes its year in a day and a half. The outermost takes about 19 days. Because the star is so dim, this closeness is not a death sentence. It is the habitable zone itself, compressed. 3 of the planets, and by some analyses 4, orbit at distances where a world with an atmosphere could keep liquid water on its surface. The planet called TRAPPIST-1e is the most promising, receiving close to the same energy from its star that Earth receives from the Sun. Its density, measured from the way the 7 worlds tug on one another, is consistent with rock, and possibly with a world that holds water in serious quantities. Then there is the clockwork, which may be the most quietly beautiful fact on this entire list. The 7 planets are locked in what astronomers call a resonance chain, the longest ever found. Their orbital periods form near-perfect whole number ratios with one another. For every 8 orbits of the innermost planet, the second completes almost exactly 5, the third almost exactly 3, the fourth exactly 2. The pattern continues down the whole family. This is not a coincidence. It is a fossil of the system's birth, evidence that the 7 worlds formed farther out and migrated inward together, gently, settling into a gravitational cord that has held them stable for billions of years. Some musicians have translated the orbits into actual notes, and the system plays a genuine harmony. 40 light-years away, 7 worlds have been keeping time together since before complex life existed on Earth. Standing on one of them would rearrange your sense of what a sky is. From the surface of TRAPPIST-1e, the star would hang huge and salmon-colored, several times the apparent size of our Sun, in a sky at permanent dusk. And the neighboring planets would not be dots. At their closest approaches, they would appear larger than our full moon, close enough that you could watch their surfaces turn with your naked eye. If clouds and continents exist there, a person on planet E could follow the weather on planet F the way we follow the phases of the moon. 7 worlds, all within sight of one another, like houses on a street. Now for the honesty this list promised, because the reference point for this system in popular retellings often drifts somewhere the evidence does not go. In the years after the discovery, stories circulated about strange light patterns around TRAPPIST-1, dimming that did not match the planets, whispers of something artificial. The real explanation is well understood and needs no embellishment. TRAPPIST-1 is a flare star, prone to sudden outbursts, and 7 overlapping transits produce a light curve of genuine complexity. The apparent misbehavior of the star's light was the star's own temper, plus the crowded traffic of its family. No structures, no satellites' shadows. What the flickering actually revealed, when it was fully untangled, was better than the rumor. It was 7 real worlds. On this countdown, that trade will happen more than once. The mundane explanation, followed honestly, keeps turning out to be extraordinary. The open question, and it is genuinely open, is whether those 7 worlds kept their air. Red dwarfs are gentle for trillions of years, but violent in their youth, whipping their close-orbiting planets with flares and radiation that can strip an atmosphere away entirely. This is the single most important unknown about the most common kind of star in the galaxy, and the James Webb Space Telescope is answering it right now, planet by planet. The early verdicts are sobering. Planet B, the innermost, appears to have no meaningful atmosphere at all. Webb measured the heat glowing from its day side, about 230 degrees Celsius, the signature of bare, airless rock. Planet C likewise shows no sign of the thick carbon dioxide blanket a Venus-like world would wear. 2 worlds in, the score reads like a warning. But the habitable zone worlds, E and F and G, are farther from the star's temper, and their verdicts are still being gathered. Webb's measurements there are harder, at the very edge of the telescope's abilities, and the honest status is pending. Hold that word. Within this decade, we may know whether a temperate, Earth-sized planet around a red dwarf can keep an atmosphere. Because red dwarfs make up roughly 3 out of every 4 stars in the galaxy, the answer multiplies across hundreds of billions of star systems. If the answer is yes, then the most common star in the universe comes with livable real estate as a standard feature, and the census from our previous item was an undercount. If the answer is no, then the galaxy's quiet majority of stars sit next to sterile stone, and sun-like stars carry the hopes alone. Either answer rewrites the odds of company, and the instrument that decides it is flying right now. Notice, before we move on, that our checklist from the census has started to sharpen. Water, restless chemistry, ordered signal. TRAPPIST-1 hands us the candidate worlds by the handful and pins the first item of the checklist, liquid water, on the verdicts to come. 7 addresses, 3 of them promising, around a star that will outlive every sun like ours. The universe did not just build worlds in abundance. It builds them in convenient clusters, wrapped in harmony, around stars that last practically forever. It helps to understand why red dwarfs sit at the center of this whole discussion, because their importance is easy to underrate. When most of us picture a star, we picture something like the Sun, a warm yellow globe. But the Sun is not typical. The typical star in the galaxy is a red dwarf, small, cool and dim, and they are not a minor category. Roughly 3 out of every 4 stars in the Milky Way are red dwarfs, which means that when you ask where most of the galaxy's planets live, the answer is overwhelmingly around stars like this one. If Earth-like conditions are possible around red dwarfs, then the habitable real estate of the galaxy is not spread evenly across all stars. It is concentrated around the small ones, and the small ones are almost everywhere. This is why a single system 40 light-years away commands so much of the world's biggest telescope time. TRAPPIST-1 is not just one interesting star. It is the nearest, clearest test case for the most common habitable situation in the universe. The reason the 7 worlds could be weighed so precisely is itself a piece of the system's strangeness, and it rewards a moment's attention. Because the planets orbit in that tight resonance chain, they tug on one another as they pass, and each tug slightly speeds up or delays the next planet's transit. Astronomers measured those tiny variations in timing, some only minutes long, and worked backward to the masses that must be producing them. From transit timing alone, the team extracted the weight of each world, and the weights came back low, consistent with rock, and, for several of the planets, with a meaningful fraction of water, perhaps far more water by proportion than Earth carries. These may be worlds with deep global oceans, or thick ice, or both. The measurement was possible only because the planets are packed so close that they meddle in one another's clocks, which is the same closeness that makes their sky so crowded and their history so intertwined. There is a sobering counterweight, to keep honest, and it is the flip side of the red dwarf's near immortality. A star that burns slowly for trillions of years is stingy and cool in maturity, but it is wild in youth, and its youth lasts a long time. Before it settles down, a red dwarf can spend 1 billion years or more flaring violently, hurling ultraviolet radiation and charged particles at the very planets orbiting close enough to be warm. Those flares can strip a planet's atmosphere away molecule by molecule, or drive its water into space, leaving a warm rock with no air and no sea. TRAPPIST-1 is old enough now to be calm, but its planets had to survive that long, stormy adolescence. Whether they did is not a matter of opinion but of measurement, and it is precisely the measurement the James Webb Space Telescope is making, world by world, right now. The system is not a fantasy of 7 guaranteed Edens. It is a real experiment with the atmospheres as the variable, and the results arriving on a schedule set by telescope time and the patience of the astronomers who fought for it. One more feature of the system rewards a moment of wonder, because it turns the whole family into a single connected place rather than 7 separate worlds. Because the planets are tidally locked to their star, each most likely keeps one face turned permanently toward TRAPPIST-1, a day side in eternal salmon light and a night side in eternal dark, with a ring of perpetual twilight running between them where a temperate climate might gather. And because the worlds orbit so close together, they exchange more than gravity. Any meteor strike large enough to blast rock off one planet would fling that rock, on occasion, onto its neighbors, far more easily than material ever crosses the gulfs of our own solar system. If life ever arose on even one of the 7, the physics of the system makes it plausible that it could have been seeded, hitchhiking on ejected stone, to the others. The whole family could share a single biology, or fail to share it, and either outcome would be one of the most important things we could learn. 7 worlds, close enough to trade rocks, is not just a crowded sky. It is a natural experiment in whether life, once started, spreads. It is also worth naming honestly what the pending verdicts will and will not tell us, so that the eventual news is heard correctly. When the James Webb Space Telescope finishes its work on planets E, F, and G, it will not announce life. It is measuring atmospheres, whether these temperate worlds kept any air at all, and if so, roughly what it is made of. A finding of a substantial atmosphere on a habitable zone TRAPPIST world would be historic on its own, because it would prove that a rocky planet can survive its red dwarf's stormy youth with its air intact, and that would resurrect the hopes for the galaxy's most common stars in a single stroke. A finding of no atmosphere, world after world, would be a quieter and sadder result, a hint that close-in planets around flaring dwarfs are stripped bare, and that the census of the previous item, however enormous, may need to lean more heavily on rarer, gentler stars like our Sun. Either way, this is the value of the system. It is not a promise. It is a decisive test, running now, of the single most important question hanging over the abundance of habitable worlds. And yet, for all the promise of that little system, the strongest evidence for habitable water anywhere beyond Earth is not 40 light-years away. It is not even 1 light-year away. It is parked in orbit around Saturn, less than an hour and a half from here at the speed of light, and a spacecraft built in the 1990s has already flown through it, tasted it, and sent the analysis home. Number 8. The oceans next door. Every conversation about life beyond Earth eventually arrives at water, and for good reason. Water is the solvent of biology, the medium where chemistry becomes metabolism. For most of the 20th century, the assumption was simple. Liquid water needs warmth. Warmth comes from sunlight, and so the search for living worlds meant the search for planets at just the right distance from their stars. Our own solar system, by that logic, had exactly one interesting address, and we live there already. Mars, perhaps, in its ancient past. Everything beyond the asteroid belt was written off as frozen scenery. That assumption did not survive contact with Saturn. In 2004, after a 7-year voyage, NASA's Cassini spacecraft slid into orbit around the ringed planet and began the most productive tour of another planetary system ever conducted. Cassini would spend 13 years there, and among its hundreds of discoveries, one small moon rewrote the rulebook. Enceladus is a bright white ball of ice about 500 kilometers across, roughly the width of Arizona. It is so small that its gravity is feeble, so cold at the surface that ice behaves like granite. Nobody expected anything from it. On the short list of places to find liquid water, Enceladus did not appear at all. Then, in 2005, Cassini's instruments noticed something impossible. Enceladus was leaking. Flying near the moon's south pole, the spacecraft detected a bending of Saturn's magnetic field, the kind caused by an atmosphere, except the disturbance was concentrated at one pole. Cameras were re-aimed, and there it was, backlit by the sun. Geysers. Fountains of water ice, erupting continuously from 4 long parallel fractures near the South Pole, gashes that mission scientists nicknamed the Tiger Stripes. The plumes rise hundreds of kilometers, and the fraction that escapes the moon's weak gravity goes on to form one of Saturn's rings, the E-ring, a fact that had been photographed for years without anyone realizing they were looking at a moon's ocean, sprayed across space. An ocean is exactly what it turned out to be. By tracking a tiny wobble in the moon's rotation, scientists established that the ice shell of Enceladus is not frozen to the rock beneath. It floats. Underneath the ice lies a global ocean of salt water, kept liquid not by sunlight but by tides. Enceladus orbits Saturn in a gentle gravitational tug-of-war, stretched and squeezed on every loop, and that constant kneading heats its interior the way a wire warms when you bend it back and forth. The sun has nothing to do with it. The rulebook that said liquid water needs a nearby star was wrong, and the corrected rule multiplies the places life could live by an enormous factor. Any icy moon around any giant planet, around any star, anywhere, at any distance, can hold an ocean if tides need it. What makes Enceladus the single best laboratory in the solar system is that its ocean does not hide. It comes up to meet you. In October of 2015, mission controllers steered Cassini into the boldest maneuver of the mission, a dive directly through the plume, just 49 kilometers above the surface. Put yourself aboard for that pass. The spacecraft comes in fast, at roughly 30,000 kilometers per hour, and below it, the little moon is blinding white, scarred with those 4 blue-green fractures. Ahead, lit from behind by the distant sun, the fountains rise in slow motion, curtains of ice crystals climbing into black space, higher than the moon is wide. Saturn hangs pale and enormous in the distance, its rings a thin, bright line. Then the spacecraft threads the fountain. Ice grains patter against the instruments, each one a tiny frozen droplet of an alien sea, minutes removed from the water below. There is no sound, no shudder, just a machine built by human hands, flying through the spray of an ocean no eye has ever seen, catching seawater on its tongue. The analysis of that spray, gathered across the mission's many passes, reads like a checklist being filled in line by line. Salts, detected in 2009, proving the water is in contact with rock, leaching minerals the way Earth's oceans do. Tiny grains of silica, whose specific size, it was argued, forms only in hot water, evidence of hydrothermal activity on the seafloor, the same kind of vents that host thriving ecosystems in Earth's sunless depths. Then, in 2017, the finding that made astrobiologists sit up straight: molecular hydrogen gushing in the plume. Hydrogen in that setting is food. At Earth's seafloor vents, microbes eat exactly that molecule, combining it with carbon dioxide in a reaction that powers whole communities of life without a single ray of sunlight. Enceladus was not just wet. Its ocean had a stocked pantry, and the pantry was being restocked continuously by chemistry at the seafloor. The list kept growing after the mission ended, because Cassini's data outlived Cassini. In 2023, scientists sifting the spacecraft's measurements of Saturn's E-ring found phosphates, compounds of phosphorus, in ice grains that came from Enceladus. Phosphorus was the last of the 6 essential elements of life, still missing from the moon's inventory, the element that builds DNA's backbone and every cell's energy currency, and it was there, apparently at concentrations far higher than Earth's oceans. Then, in 2025, a fresh analysis of the ice grains from that 2015 plume dive, the freshest samples of all, grains only minutes out of the ocean, revealed families of organic molecules never before seen there, including compounds carrying nitrogen and oxygen. On Earth, molecules of those families sit in the middle of the chemical pathways that lead toward the complex machinery of biology. None of this is a detection of life, and this list will not pretend otherwise. What it is a completed habitability checklist: liquid water, an energy source, organic chemistry, all 6 essential elements. Every requirement biology has, verified, on a moon the width of Arizona, by a spacecraft whose instruments were designed before anyone knew the plumes existed. And Enceladus may only be the 2nd best ocean in the neighborhood. Jupiter's moon Europa, nearly the size of our own moon, wears a shell of ice 15 to 25 kilometers thick, crisscrossed with rust-colored cracks. Beneath that shell, measurements of Jupiter's magnetic field flexing through the moon reveal a salty ocean holding roughly twice as much liquid water as all the oceans of Earth combined. Twice the water of Earth, on one moon, kept warm by the same tidal kneading. The Hubble Space Telescope caught what appeared to be water vapor plumes above Europa in 2012 and again in 2016. And in a detail that deserves more fame than it has, scientists went back in 2018 to data from the old Galileo spacecraft, which had swung close past Europa in 1997 and realized its instruments had recorded a signature best explained by the spacecraft having flown through a plume 20 years before anyone knew to look for one. The sample was collected before the question was asked. Nobody was listening at the time. The follow-up is already flying. In April of 2023, the European Space Agency launched JUICE, the Jupiter Icy Moons Explorer, arriving at the Jupiter system early in the next decade to survey Europa, Callisto, and especially Ganymede, the largest moon in the solar system, which likely hides an ocean of its own. And in October of 2024, NASA launched Europa Clipper, the largest spacecraft the agency has ever built for a planetary mission, its solar arrays spanning more than a basketball court. Clipper arrives in 2030 and will make dozens of close passes over Europa, mapping the ice, sniffing for plumes, and measuring whether the ocean below can support life. Add Titan, Saturn's giant moon, with its rivers and seas of liquid methane and its own buried water ocean, where NASA's Dragonfly rotorcraft is scheduled to fly in the 2030s, and the outer solar system stops looking like frozen scenery. It looks like an archipelago of hidden seas, with missions en route. Step back and weigh what this item does to the odds. Our solar system was supposed to contain one wet world. It contains, by current count, at least half a dozen bodies with strong evidence of liquid water, most of them owing nothing to the sun's warmth. If tides can keep oceans liquid, then oceans do not need habitable zones, and the number of potential cradles in the galaxy is not 300 million. It is billions upon billions, orbiting every kind of star, including the dead ones. The nearest possibly habitable ocean is not a telescope target at all. It is a destination, a spacecraft ride away, and it is actively handing out free samples to anyone who flies through the spray. The only thing missing is an instrument designed to answer the direct question, because Cassini, for all its brilliance, carried nothing built to detect life itself. The sample sits in the sky, waiting for the right laboratory to be sent. It is worth understanding the tidal engine a little more deeply, because it is the mechanism that pried the search for life loose from the habitable zone entirely. Imagine a moon on a slightly stretched orbit around a giant planet. When it swings closer to the planet's gravity pulls on its near side harder than its far side, and the moon deforms, bulging along the line to the planet. When it swings farther away, the pull eases, and the moon relaxes toward round. Over one orbit, the whole body is flexed and released, and because this happens on every orbit, forever, the flexing never stops. Solid rock and ice resist that flexing, and resistance makes heat, the same way a paperclip bent back and forth grows warm at the crease. On Enceladus, on Europa, on Io, this tidal heating pours energy into the interior with no sunlight involved whatsoever. It is gravity, converted to warmth, keeping oceans liquid hundreds of millions of kilometers from any star. And giant planets with orbiting moons are common across the galaxy. Wherever they exist, this engine can exist, which means liquid water can exist in the frozen dark, far outside any star's warm band, around dim stars, around dead stars, in the great cold majority of the galaxy that the old habitable zone thinking wrote off completely. The specific chemistry Cassini found at Enceladus deserves to be spelled out, because each molecule is a rung on a ladder that leads on Earth in only one ultimate direction. Start with the water itself, salty in almost the same proportion as Earth's seas. Add the silica nanograins, whose size, the analysis argued, forms only when hot water, above about 90 degrees Celsius, interacts with rock and then cools quickly, the fingerprint of active hydrothermal vents on the seafloor below. Add molecular hydrogen, the fuel, produced when that hot water reacts with rock in a process that on Earth feeds entire ecosystems in the sunless deep. Add carbon dioxide, The raw material, those same ecosystems combine with hydrogen to make methane and, ultimately, the molecules of life. Add ammonia, a nitrogen source. Add the phosphates found in 2023, the phosphorus for genetic material and cellular energy. Then, in 2025, add the fresh organic molecules pulled from grains only minutes out of the ocean, molecules bearing the reactive chemistry that on Earth sits partway along the road from simple carbon compounds to the complex machinery of a cell. Line those findings up, and what you have is not merely a habitable ocean, but an ocean already running the opening moves of the exact chemistry that, on our planet, ended in life. Nobody claims it has taken the final step. But a small moon of Saturn has assembled, in plain view of a passing spacecraft, very nearly every ingredient and process on the recipe. The frustration built into this item is the same one that runs through the whole night, and it is worth stating without drama. Cassini was a spectacular machine, but it was conceived and built in the 1980s and 90s, before anyone knew the plumes existed, and it carried no instrument designed to detect life directly. It could taste the ocean's chemistry, weigh its molecules and map its warmth, but it could not look for a living cell, because nobody who built it knew there would be an ocean to look in. When its mission ended in 2017, controllers deliberately steered it to burn up in Saturn's atmosphere, for a reason that belongs on a list about life. They were afraid that the aging spacecraft, if left to drift, might one day crash into Enceladus or Europa, and contaminate a pristine alien ocean with hardy Earth microbes hitchhiking from the factory floor. That single decision, to destroy a working spacecraft rather than risk polluting a possible biosphere, is itself a quiet measure of how seriously the possibility is now taken. The next spacecraft, purpose-built, will carry the instruments Cassini lacked. Until then, the ocean keeps spraying its free samples into space, unread, minutes fresh, waiting. There is a comparison worth drawing here between these hidden oceans and the only place we know life definitely lives, because it reframes what counts as a promising address. On Earth, the deepest, darkest, most sunless environments, the hydrothermal vents on the ocean floor, are not barren. They teem. Whole ecosystems thrive there in perpetual darkness, built not on sunlight but on chemistry, on the hydrogen and minerals that pour from cracks in the seafloor, exactly the chemistry Cassini detected at Enceladus. Many scientists suspect that life on Earth may have begun in precisely such a place, in the warm, mineral-rich water around a deep-sea vent, rather than in some sunlit pond. If that is true, then the sunless oceans of Enceladus and Europa are not poor imitations of Earth's surface. They are close copies of the very setting where life on our own planet may have taken its first step. The habitable zone, the warm band around a star, was always a surface dweller's prejudice. The oceans that matter most may be the ones that never see their star at all. The scale of Europa's ocean in particular is worth sitting with, because it upends our intuitions about where the water is. We think of Earth as the water world, the blue planet, and in terms of surface area it is. But Earth's oceans are a thin film, on average only a few kilometers deep, spread over a rocky ball 8,000 kilometers across. Europa, a moon smaller than our own, holds beneath its ice a global ocean estimated at 60 to 150 kilometers deep, and by volume, it contains roughly twice as much liquid water as all of Earth's oceans combined. Twice the water of Earth, on a moon you could hide inside our planet many times over, kept liquid by nothing but the flexing grip of Jupiter's gravity. And Europa is only one of several such moons. Ganymede, the largest moon in the solar system, likely holds an even greater volume of water, buried deeper still. When you add up the hidden seas of the outer solar system, the moons hold vastly more liquid water than all the sunlit surfaces of the inner planets put together. The water of our solar system is not mostly here, on the warm blue planet. It is mostly out there, in the cold and the dark, locked under ice, needed by tides. So the ingredients are everywhere. Water in abundance, energy without sunlight, the elements of biology stocked in an ocean next door. Which is exactly why the next item on this list is so much harder to wave away. Because if the kitchen is stocked all over the galaxy, then a strange signal from the direction of Sagittarius, at precisely the frequency a civilization would choose, deserves to be taken seriously. In 1977, such a signal arrived. It lasted 72 seconds. We are still talking about it. Number 7. The WOW signal. To understand why 72 seconds of radio noise from 1977 still matters, you first have to understand a prediction made 18 years earlier. In 1959, two physicists at Cornell University, Giuseppe Cocconi and Philip Morrison, published a short paper asking a practical question. If a civilization around another star wanted to be noticed, how would it call? Radio, they reasoned, crosses the galaxy cheaply and at the speed of light. But radio is a dial with millions of channels. A signal is useless if nobody knows where to tune. So the two physicists looked for a channel that every scientist in the galaxy would know, regardless of their biology, their language, or their history. There is exactly one obvious answer. Hydrogen is the most abundant substance in the universe, and every hydrogen atom everywhere occasionally hums at one precise natural frequency, 1420 megahertz, a wavelength of about 21 centimeters. Every radio astronomer in the universe discovers this hum, because it is how you map the galaxy's gas. It is the universal channel marker, written into physics itself. If you wanted to be found, Cocconi and Morrison argued, you would broadcast there, or close to it, because that is where everyone listens. The paper closed with a line that has never stopped being quoted. The probability of success is difficult to estimate, but if we never search, the probability of success is 0. People searched. Among the searchers was a giant and mostly forgotten instrument in the farmland of Delaware, Ohio, run by Ohio State University. The Big Ear was not a dish. It was a fixed reflector of aluminum mesh, 3 football fields in size, laid out across the ground like a metal meadow. It could not steer or track. It simply faced the sky and let the Earth's rotation sweep its narrow beam across the heavens, a slow scan of the entire visible sky, night after night, year after year. By the 70s, its funding was so thin that the survey ran essentially on volunteers, and the data spooled out of a computer onto fanfold printer paper, columns of numbers recording the radio brightness of the passing sky, near the hydrogen frequency, to be reviewed by human eyes days later. One of those volunteers was an astronomer named Jerry Eman. On August 15, 1977, nobody was watching the sky at all. The telescope stared, the computer recorded, the paper piled up. Several days later, Eamon sat down, likely at his kitchen table, with a stack of printout, doing the unglamorous work of scanning column after column of low digits, 1s and 2s, the ordinary breathing of the radio sky. Picture the scene, because this is one of the great moments in the history of listening. A quiet suburban evening in Ohio. Fanfold paper folded over itself in stacks. A man in reading glasses, running his eye down numbers, page after page, the way he had done for years. And then his eye snags. In one narrow channel, at one moment, the numbers do not read 1 or 2. They climb, character by character, 6, E, Q, U, J, 5, and fall away again. On that printout scale, where digits ran 0 through 9 and then continued into letters, a U meant a signal roughly 30 times louder than the background of the sky. Eamon had never seen anything like it. Nobody at Big Ear had in years of scanning. He picked up a red ballpoint pen, circled the 6 characters, and wrote a single word in the margin. Wow. The name stuck, because nothing about the signal has ever stopped deserving it. Consider, one property at a time, what that column of characters recorded. The signal sat almost exactly at the hydrogen frequency, the universal channel marker, precisely where Cocconi and Morrison predicted a deliberate beacon would sit. It was narrowband, its energy squeezed into a sliver of the dial. Nature is sloppy with its radio. Gas clouds, flaring stars, pulsars, all of them smear their emission across wide swaths of spectrum. Transmitters concentrate. A signal that narrow is, by every standard we use, the signature of equipment, and that particular slice of the dial is legally protected on Earth, reserved for astronomy, with transmitters forbidden. It rose and fell over exactly 72 seconds, and that number is the quiet masterpiece of the whole story. Big Ear could not track. Its beam swept the sky at the rotation rate of the Earth, and any true point on the sky would take exactly 72 seconds to cross the beam, growing louder as it entered, peaking at dead center, fading as it left. The wow signal traced that curve perfectly. It was not a glitch in the electronics, not a passing aircraft, not a satellite streaking through. It was something out there, parked on the sky, shining steadily while the Earth's rotation carried the telescope's gaze across it. The signal was on before the beam arrived. It was still on when the beam moved past. It came from the direction of Sagittarius, near a scatter of stars called Key Sagittarii, looking toward the crowded heart of the Milky Way. And then it was never heard again. That absence is the wound that has never closed. Big Ear itself had a built-in second chance. Its receiver watched through 2 adjacent beams, and the same patch of sky should have crossed the second beam about 70 seconds later. Silence. Either the signal switched off in that 1 minute, or it was beamed narrowly and swept away, like a lighthouse turning. In the months and years that followed, Big Ear returned to those coordinates more than 50 times. Nothing. The Very Large Array in New Mexico, one of the most powerful radio observatories on Earth, listened. Nothing. Later searches with modern equipment have rescanned the spot again and again. The sky in Sagittarius has stayed ordinary for nearly 50 years. Every mundane explanation has been dragged to the witness stand, and each has struggled. Earthly interference does not fit. The frequency is protected, and the 72-second rise and fall matches a source fixed on the distant sky, not a transmitter on the ground or a satellite crossing above. In 2017, one researcher proposed that a pair of comets, trailing clouds of hydrogen, had drifted through the beam. The idea made headlines and did not survive review. Comets do not shine brightly in narrowband at that frequency, and the geometry placed them in the wrong part of the sky. More recently, astronomers combing old archives have offered a subtler natural candidate, a rare flare, perhaps from a magnetar, briefly lighting up a cold cloud of hydrogen and making it blaze at that exact frequency, like a natural laser. It is a clever mechanism, honestly labeled by its own authors as tentative, and it has a cost either way. If it is right, the sky performs single-use tricks at the hydrogen line that we have caught exactly once. If it is wrong, the leading natural explanation is still unwritten. So the scorecard, after 5 decades, reads like this. The wow signal remains exactly what a one-time sweep of another civilization's transmitter across Earth would look like. It also remains exactly what a rare, still unmodeled natural flare would look like. Both of those sentences are true at the same time, and the discipline of this list requires saying both. What the signal is not, is explained. The human story threaded through it deserves its moment too, because it says something about what honesty looks like. Jerry Amon, the man who wrote Wow, spent the rest of his life as the discovery's most careful skeptic, warning audiences, in his phrase, against drawing vast conclusions from half-vast data. He never claimed aliens. He only declined, decade after decade, to accept explanations that did not fit the numbers on his printout. There is a quiet integrity in that, a man guarding a mystery from both kinds of corruption, the debunkers and the believers alike. Meanwhile, the telescope itself met a very American fate. Big Ear's land became too valuable, and in 1998, the great aluminum meadow was torn down. The site is now part of a golf course. The strongest candidate signal in the history of the search for extraterrestrial intelligence was received by an instrument that no longer exists, on ground where people now play through, and the entire physical evidence of that night consists of a strip of 1970s printer paper with 6 characters circled in red, resting in an archive in Columbus, Ohio. Hold on to the number, though. 72 seconds. It was not chosen by whoever or whatever transmitted. It is simply how long the turning Earth allowed one fixed telescope to listen at one point of sky. Any single observer, catching any steady signal, hears only the slice their own geometry permits. 72 seconds is what a fragment sounds like, the size of a keyhole between two worlds. Remember it when we reach number 1, because by then you will know who else's keyhole we might be shining through. To feel the full weight of that 72 seconds, it helps to understand exactly how the Big Ear worked, because the telescope's own design is what makes the signal so hard to dismiss. The instrument had 2 feed horns, 2 separate ears, pointed at slightly different patches of sky. As the Earth turned, any fixed celestial source would drift first through one horn's field of view and then, some minutes later, through the others. This gave every detection a built-in verification. A real object in the sky must show up twice, in both horns, separated by the right interval. And it gave the response its characteristic shape. Because the beam was widest at its center and tapered at its edges, a steady source would appear to rise in brightness as it drifted into the beam, peak as it crossed the center, and fall as it drifted out, over that fixed 72-second window set by the Earth's rotation. The WOW signal drew that curve to perfection. It rose, it peaked, it fell, exactly on schedule for a genuine point on the sky. This is why local interference was ruled out early. A transmitter on the ground, an aircraft, a passing satellite, would not paint the sky's own drift curve. The signal had the fingerprint of the heavens on it, the unmistakable signature of something sitting still out among the stars while the planet turned beneath it. But there is a genuine puzzle inside that verification, and honesty requires facing it, because it cuts against the artificial reading as much as for it. If the source drifted through the beams the way a real celestial object should, then it should have appeared in the second horn as well, 70 or so seconds after the first. It did not. The record shows the signal in one horn and silence in the other. There are 2 ways to read that gap, and neither is comfortable. Either the signal switched off or dropped below detectability in the roughly 1-minute interval between the 2 ears, which is strange behavior for a steady natural source, but ordinary behavior for something pulsed or swept, like a beam that had turned away. Or there is a subtlety in exactly which horn was which and when, a bookkeeping question that researchers have argued over for decades without full resolution. What is not in dispute is the core shape. For 72 seconds, at the frequency the whole galaxy is presumed to share, something narrow and strong and celestial poured into the Big Ear, and then it was gone, and it has never, in half a century of listening, come back. The frequency detail deserves one more pass, because it is the single most suggestive fact in the entire episode. The hydrogen line sits at 1420 megahertz for a reason woven into the structure of the atom itself, and every technological species that develops radio astronomy will discover it, because it is how you map the cold hydrogen gas that fills every galaxy. This makes it the one frequency you can assume a stranger knows. There is even a poetic extension of the idea, sometimes called the water hole, the quiet band of the radio spectrum between the natural emission frequencies of hydrogen and the hydroxyl molecule, the two pieces that together make water. The reasoning runs that water-based life might choose to meet at the frequencies named for water's own components, a natural gathering place, quiet and obvious to anyone who thinks the way we think. The wow signal landed remarkably close to hydrogen's own note. Whoever designed a beacon would put it there. And so would nature. If nature had a rare trick at that frequency, we have simply never caught in the act more than once. The frequency is the strongest argument for artificiality, and, at the same time, the exact place a rare natural hydrogen flare would be brightest. The clue points both ways with equal force, which is precisely why 50 years of argument have not settled it. It is worth reflecting on what the never-repeating quality actually does to our ability to know anything, because it is the deepest source of the frustration. In every other science, a surprising result can be checked by repeating the experiment. See something once, and you look again, and again, until you either confirm it or explain it away. The wow signal denies us that entirely. It happened once, was recorded by a machine while no human watched, and then refused every attempt to make it happen twice. This is why it can never be promoted to proof, and also why it can never be fully dismissed. A single, unrepeatable event sits permanently in a kind of purgatory, too clean and too well recorded to ignore, too solitary to confirm. If it was a civilization sweeping a beam across our sky, we caught the one instant the beam happened to cross Earth, and it moved on, or switched off, or was never aimed at us in the first place, and we will wait forever for a repeat that was never promised. If it was a rare natural flare, we caught the one time it fired at the one frequency we were watching. Either way, the universe granted us exactly one look and then closed the door, and half a century of listening has not persuaded it to open again. Consider, too, the strange smallness of the physical record, because it says something about how fragile our grip on these moments really is. The most famous candidate signal in the history of the search for other minds does not exist as a sound file, or a photograph, or a piece of hardware. It exists as ink on paper, a strip of green and white fanfold computer printout, the kind that spooled out of machines in the 1970s, with a column of characters reading 6EQUJ5, and beside them, in a man's handwriting, in red ballpoint, the word wow and an exclamation point. That strip of paper is now among the most carefully preserved documents in the field, kept in an archive at Ohio State University, and it is, quite literally, the entire physical evidence of the event. The telescope that recorded it is gone, its aluminum meadow torn up, the ground turned into a golf course. If that fragile page were ever lost, nothing tangible of that night would remain but memory. It is a humbling thought that the strongest hint we may have ever received of company in the universe rests, in the end, on a single sheet of decades-old printer paper, guarded like a relic, holding a mystery no one has been able to close. A signal, in the end, is information without a body, and its frustration is that you cannot walk over and touch it. The next sign on our list solves that problem completely. It is a piece of another world, 4.5 pounds of it, and you could hold it in your 2 hands. It was found lying on the ice at the bottom of the Earth, and for one summer in the 1990s, it convinced the White House that we had found the neighbors. Number 6. The rocks that look alive. Antarctica is the best meteorite trap on Earth. Stones that fall anywhere else vanish into forests, oceans, and soil, but stones that fall on the East Antarctic ice sheet are carried along inside the slowly flowing ice, and in certain places where the flow runs up against buried mountains, the ice stalls, the wind strips it away layer by layer, and everything it carried is left sitting on the surface. Dark rocks on blue-white ice, sometimes tens of thousands of years after they fell. Every southern summer, teams of scientists ride snowmobiles across these stranding zones, collecting the sky's droppings, and on December 27, 1984, a meteorite hunter named Roberta Score spotted a stone that stood out even there. It was about the size of a large grapefruit, 4.5 pounds, and oddly greenish in the polar light. Following procedure, she bagged it without touching it. It was catalogued as the first find of the season from the Allen Hills region, and given the name that would later be spoken in the White House. Allen Hills 84001. The rock sat in a Houston cabinet for nearly a decade before anyone realized what it was. When scientists finally analyzed the gases trapped in its glassy pockets, they matched, measurement for measurement, the atmosphere of Mars as sampled directly by the Viking landers in the 1970s. The stone was a piece of Mars. Its deeper history, read from its minerals, is itself a small epic. It crystallized about 4 billion years ago, making it a fragment of Mars's primordial crust, formed when the red planet was young, wet, and warm. Roughly 17 million years ago, an asteroid struck Mars hard enough to throw fragments clean off the planet, and this one wandered the solar system until about 13,000 years ago, when it fell onto Antarctic ice while humans were still painting caves. A messenger from Mars's habitable youth, delivered by orbital mechanics, free of charge. Then came August 7th, 1996. A team of NASA scientists led by David McKay published a paper in the journal Science, making the most careful version of an incautious claim. Inside Allen Hills 84001, they reported 4 separate lines of evidence, which taken together, they interpreted as possible traces of ancient Martian life. There were carbonate globules, tiny orange disks of a mineral that forms in liquid water. There were organic molecules of the family called PAHs, scattered in and around the carbonates. There were crystals of magnetite, an iron mineral, in sizes and chain-like arrangements resembling those grown by certain Earth bacteria, which use them as compass needles. And there were the pictures, the ones that traveled around the world. Under the electron microscope, the rock's surfaces showed tiny, segmented, worm-like forms, 20 to 100 nanometers long, that looked for all the world like fossilized microbes. The announcement went off like a cultural depth charge. President Clinton stepped onto the south lawn of the White House that same day and addressed the planet about a rock. "If this discovery is confirmed," he said, "it will surely be one of the most stunning insights into our universe that science has ever uncovered." For one summer, much of humanity walked around quietly believing that the answer had arrived, that we were the descendants of a solar system that made life at least twice. Science then did what science is for. Over the following years, each of the 4 lines of evidence was tested against a hard question. Can plain chemistry, with no biology anywhere, produce this? One by one, the answers came back yes. Carbonates, like those, can form from water and rock without life. PAHs are common in space, found in meteorites nobody suspects of biology, and in interstellar clouds. Magnetite chains of the right sizes can grow through non-biological processes, including the shock of the very impact that launched the rock. And the worm-like shapes were probably never big enough to be alive in the first place. Most were tens of nanometers long, and a cell that small has no room for the minimal machinery of life. Some may simply be mineral ledges, dressed up by the microscope's coating process. The scientific consensus settled, not with a dramatic refutation but with a quiet weight of alternatives. Every feature in the rock can be explained without Martians, and so, by the standards of extraordinary claims, the claim was set down. But do not file this item under failure, because its consequences are still in motion. The Alan Hills episode forced science to write, for the first time, real rules for the hardest question it will ever answer. How much evidence, of what kind, should convince us that we are looking at alien life? The answer that emerged, line by careful line, is the standard every claim on tonight's list is now measured against. And the argument reorganized NASA itself. The push into modern astrobiology, the mantra of follow the water, the fleet of rovers that has crawled across Mars ever since, all of it descends in a straight institutional line from that green-tinged rock. One stone from the ice did not prove there was life on Mars. It built the machinery for finding out. That machinery is now parked at the most promising address on the planet, and this is where the story stops being history and becomes news. In February of 2021, NASA's Perseverance rover landed in Jezero crater, chosen because orbital images show, in unmistakable relief, a fossilized river delta spilling through a break in the crater's rim. 3.5 billion years ago, Jezero was a lake, fed by a river, holding water for spans of time long enough to matter. Perseverance is a geologist built for one purpose above all others, to find rocks that might remember that lake and to seal samples of them for a future ride home. In July of 2024, in an ancient river channel called Neretva Vallis, the rover rolled up to an arrowhead-shaped slab of reddish mudstone about a meter wide. The team named it Sheyava Falls, after a waterfall in the Grand Canyon. And on its face, the instruments found a pattern that made the science team's collective breath catch. Scattered through the rock were small pale rings with dark rims, dozens of them, a texture the geologists called leopard spots. The rims are not decoration. They are chemical reaction fronts, and their mineralogy is specific. 2 iron-bearing minerals, vivianite, an iron phosphate, and greigite, an iron sulfide, sit tangled together with organic carbon in the same spots. On Earth, that particular combination is the routine fingerprint of mud-dwelling microbes, organisms that make their living by passing electrons through iron and sulfur while consuming organic matter. And critically, the surrounding rock shows no evidence of the high temperatures or acidic conditions that would let ordinary chemistry produce the same pattern easily. Cold, gentle mud, organic carbon, and reaction rims that on our planet usually mean something was eating. Perseverance drilled the rock, sealed the core in a titanium tube, and named the sample Sapphire Canyon. The team then spent a year doing exactly what the Alan Hills rules require, trying to kill their own discovery. In September of 2025, after formal peer review, NASA made its announcement, and the language was chosen with a care that tells its own story. A potential biosignature. The clearest candidate sign of ancient life ever found on Mars. Not proof, and nobody involved says proof, because slow, cold, lifeless chemistry has not been fully ruled out and cannot be ruled out by a rover. The instruments that could settle the question, the ones that image individual microfossils and read isotopes atom by atom, are the size of rooms and live in laboratories on Earth. Which brings us to the strangest, most human twist of this whole item. The answer, or at least the best chance at an answer humanity has ever collected, is currently sealed in a titanium tube, sitting in Jezero crater, waiting. The Mars Sample Return Campaign, the mission meant to fetch Perseverance's tubes, has been redesigned, delayed, and budget squeezed repeatedly, its architecture reopened for cheaper proposals, its schedule sliding through the 2030s. The rock that made the world hold its breath in 1996 fell to Antarctica on its own, for free. The rock that might finish the job is 225 million kilometers away at its nearest, and it needs a ride we keep postponing. Think of the two bookends of this story as one arc. In 1984, a woman in a red parka bends down on blue ice and picks up a green stone that will make a president speak of other worlds. 40 years later, a robot the size of a car cuts a plug from a Martian riverbed, while its builders, watching from another planet, celebrate a discovery they may not live to see confirmed. Careers begin and end inside this question. The people who sealed Sapphire Canyon know perfectly well that the tube may come home to a laboratory staffed by people who are in elementary school right now. They sealed it anyway. That is what the search looks like from inside a single human lifetime, patience practiced across generations, an inheritance of carefully preserved maybes. The deeper legacy of the Allen Hills Rock is a phrase that now governs the entire field, and it is worth learning because it will decide how the next great announcement is received. In the aftermath of the 1996 claim, as each line of evidence was chipped away, the astronomer Carl Sagan popularized a principle that had circulated for years. Extraordinary claims require extraordinary evidence. No single mineral, no lone microscope image, no one measurement, however impressive, is enough to establish something as momentous as a second genesis of life. The bar is deliberately, almost punishingly high, and the Allen Hills Rock is the reason it is written the way it is. Every one of its 4 lines of evidence was real. The carbonates were there. The organic molecules were there. The magnetite chains were there. The tiny shapes were there. And still, taken together, they did not clear the bar, because for each one, an explanation without life existed. That is the lesson the field absorbed. The question is never merely, could this be life? The question is, could this be anything else? And only when the answer to the second question is a confident no, does the first question get to stand. It is worth pausing on how astonishing the delivery system itself is, because the fact that we possess a piece of Mars at all is a small miracle of physics. To launch a rock off Mars requires an impact violent enough to accelerate solid stone past the planet's escape velocity, roughly 5 kilometers per second, without simply vaporizing it. That is a narrow window, a blow hard enough to throw, but not so hard as to destroy. The fragment then drifts through interplanetary space for millions of years, its orbit slowly reshaped by the sun's gravity, until, by pure chance, its path intersects Earth's. Then it must survive the fall through our atmosphere, the fireball, the deceleration, and come to rest somewhere it will not immediately rot or bury or wash away. The Antarctic ice sheet is very nearly the only place on Earth that satisfies that last condition, preserving fallen stones for tens of thousands of years and then concentrating them at the surface. Every step in that chain is improbable, and yet we have collected a few hundred Martian meteorites, which means the chain completes often enough to keep delivering. Mars has been mailing us pieces of itself, free of postage, for as long as there has been an Earth to receive them. We simply did not know to open the envelopes until the 1980s. Return now to Shayava Falls with that history in mind, because the care in the 2025 announcement is the Allen Hills lesson made flesh. When NASA said potential biosignature, it was not hedging out of timidity. It was applying, deliberately, the exact standard that the green rock from Antarctica forced the field to adopt. The leopard spots are real. The vivianite is real. The greigite is real. The organic carbon tangled with them is real. And the absence of the high heat that would let simple chemistry mimic the pattern is real. On Earth, that specific combination in that specific cold, wet setting is a fingerprint of microbial metabolism. But could it be anything else? Could some slow, cold, purely chemical reaction, running for 1 billion years in a Martian mudstone, produce the same rings without a living thing anywhere in the process? That question has not been answered no, and it cannot be answered no by a rover 200 million kilometers away. It can only be answered in a laboratory on Earth, by instruments that image a sample atom by atom and read the isotopes of its carbon, the subtle weight difference that life leaves in the elements it uses. The sample that could carry that answer is sealed in its tube on the surface of Mars, and the ride home is the thing we keep deferring. There is a reason Jezero crater was chosen for this search out of the whole surface of Mars, and it is worth understanding because it is what makes Chayava Falls more than a random lucky rock. From orbit, Jezero shows one of the clearest fossil river deltas anywhere on the planet, a fan of sediment spilling through a gap in the crater rim, unmistakable in shape, the signature of a river emptying into a standing lake. On Earth, deltas are among the finest preservers of ancient life, because their fine muds bury organic material quickly and gently, sealing it away from decay. A geologist hunting for the oldest traces of life on Earth would go to exactly such a formation. So when NASA sent Perseverance to Jezero, it was not wandering and hoping. It was sending a robotic field geologist to the single most promising kind of location known, an ancient lakebed fed by an ancient river, precisely the setting where, if Mars ever hosted life, the evidence would most likely be written and kept. Finding the leopard spots there is not the same as finding them in some arbitrary patch of desert. They turned up exactly where the theory said to look. And it is worth being clear-eyed about the peculiar cruelty of the current situation, because it is a genuinely strange moment in the history of exploration. For the first time, humanity has, sitting in a sealed tube on the surface of another planet, a physical sample that a large team of careful scientists has formally called the clearest candidate sign of ancient life ever found beyond Earth. The sample exists. It is real. It is drilled, sealed, catalogued, and set down on the Martian ground, or held aboard the rover, waiting. The one thing standing between that tube and a definitive answer is a rocket ride, a mission to land on Mars, collect the tubes, launch them back off the planet, and carry them home to the waiting laboratories. And that mission has been redesigned, rescoped, and pushed later again and again as its costs climbed and its architecture was reopened for cheaper ideas. So the answer to one of the oldest questions a human being can ask, are we alone, may already be collected, may already be sitting in that tube, and we cannot read it, because we have not yet built and funded the ship to go and fetch it. The evidence is in hand, and out of reach, at the same time. It is worth marking how far the Mars story itself has traveled, because it puts the current moment in proportion. When the Allen Hills rock made its announcement in 1996, we had never landed a rover capable of this kind of chemistry, and Mars was, for practical purposes, a planet we studied from orbit and from a handful of stationary landers. In the decades since, a fleet of increasingly capable machines has crawled across its surface, following the water exactly as that green rock inspired them to. Spirit and Opportunity found the mineral fingerprints of ancient water. Curiosity found an entire ancient lake environment, with the carbon, the energy sources, and the chemistry that could have supported microbial life, in a crater that once held water for millions of years. And now Perseverance has found the leopard spots. Each mission was built on the last, each one narrowing the question, until the search moved from "is there water" to "was there habitable water" to, now, "is there a potential sign of life in this specific rock?" That is not a story of repeated disappointment. It is a story of steady, patient closing in, one rover at a time, on an answer that has never been closer. A rock, though, can be argued over forever, as Allen Hills proved across 3 decades. Individual objects are single witnesses, and single witnesses can be cross-examined into stalemate. A planet's entire atmosphere is a different kind of witness. It is a chemical confession renewed every day, planet-wide, impossible to fake with one lucky mineral. And as it happens, on 3 different worlds right now, the air itself is saying things that chemistry, as we currently understand it, should not allow. Number 5. The gases that should not be there. In 1965, while NASA was designing its first missions to look for life on Mars, the agency consulted an independent-minded English scientist named James Lovelock. The plans on the table involved landing instruments to hunt for microbes in the soil, essentially taking a microscope to another planet and hoping. Lovelock told them they were thinking about it wrong. "You do not need to catch life in the act," he argued. "You need to read its exhaust." A dead planet's atmosphere settles into chemical equilibrium, every reactive gas long since consumed, the whole system run down like a wound-down clock. A living planet cannot sit still. Life eats, breathes, and excretes on a planetary scale, constantly pumping out gases that react away and must be replenished. "Look for an atmosphere out of equilibrium," Lovelock said. "Look for gases that have no right to be there." Earth is the demonstration. Our air holds 21% oxygen alongside a persistent trace of methane, and those 2 gases destroy each other. Left alone, they would react away in a geological instant, the methane within about a decade, the oxygen over a few million years, rusting into rocks and settling into stillness. They persist together for one reason only. Something keeps making both, relentlessly, in planetary quantities. Photosynthesis pours out the oxygen. Life in wetlands, oceans, and the guts of animals pours out the methane. Any chemist in the galaxy, reading Earth's spectrum from light years away, would conclude that this planet's air is being actively manufactured. That insight, now 60 years old, is the foundation of the entire modern search, and this item is about the 3 worlds where the reading has already come back strange. The first is Mars, and the molecule is methane itself. Understand the stakes first. Sunlight destroys methane. On Mars, photochemistry scrubs it from the air within about 300 years, a blink in geological time. The planet is 4.5 billion years old. If there is any methane in the Martian air today, then something on Mars made it, in effect, today. There is no such thing as leftover methane. Detection equals active source, and on Earth, the overwhelming majority of methane comes from living things. The Curiosity rover has been sniffing the air of Gale Crater since 2012 with a laser spectrometer, and its long record is a genuine puzzle. There is a faint background of methane, around 0.4 parts per billion, and it breathes. The level rises and falls with the Martian seasons, which is already odd, because simple chemistry should not care much about the calendar. On top of that background come the spikes. In late 2013 and early 2014, readings jumped roughly tenfold, to about 7 parts per billion, and lingered for months before fading. Then, in June of 2019, Curiosity recorded its record, 21 parts per billion, a transient plume that vanished within days. Small numbers, but on a planet whose air should hold none, the question is not the amount. The question is the source. And here the story turns properly strange, because Europe built a spacecraft specifically to settle it. The Trace Gas Orbiter, which began its science mission in 2018, can detect methane globally at concentrations far below what Curiosity reports from the ground. It has found, essentially, nothing. Not less methane, not different methane. No methane, down to a few hundredths of a part per billion, high in the atmosphere where the gas should mix and linger for centuries. 2 excellent instruments, both presumably working correctly, returning answers that flatly contradict each other. The reconciliations on the table are all uncomfortable. Perhaps methane seeps from the ground at night, in Gale Crater, and is somehow destroyed or trapped near the surface before it can mix upward, which requires chemistry nobody has demonstrated. Perhaps the source is geological, water reacting with iron-rich rock in a process called serpentinization, which would itself be remarkable since it requires liquid water underground. Or perhaps, and no serious scientist rules it out, something is alive down there, metabolizing in the subsurface the way methane-producing microbes thrive beneath Earth's soils. The honest status is unresolved. A planet is leaking a biology-associated gas from somewhere, seasonally, in defiance of its own atmospheric chemistry, and we have not found the tap. The second world is Venus, and the claim here detonated on September 14, 2020, when a team led by astronomer Jane Greaves of Cardiff University announced they had detected phosphine in the Venusian clouds. Phosphine is a small, vicious molecule, one phosphorus atom bound to 3 hydrogens, and its resume on Earth is short and pointed. It is made industrially, and it is made by microbes that live where oxygen is absent, in swamps, sewage, and the guts of animals. On a rocky, oxidized world like Venus, known chemistry struggles to make it at all, and the amount reported, on the order of 20 parts per billion, exceeded what volcanoes, lightning, sunlight-driven chemistry, and incoming meteor dust could plausibly supply by orders of magnitude. The team spent over a year trying to explain their own signal away, and published only when they had run out of alternatives. The location matters more than the planet's reputation suggests. Venus's surface is a furnace, hot enough to melt lead, crushed under 90 atmospheres of pressure, and no one proposes life down there. But 50 to 60 kilometers up, in the cloud decks where the phosphine signal originates, conditions are eerily gentle. The pressure is about 1 Earth atmosphere. The temperature sits near room temperature. It is, by the numbers, the most Earth-like environment anywhere in the solar system beyond Earth itself, with one spectacular caveat. The clouds are droplets of concentrated sulfuric acid, an environment that would demand biochemistry far hardier than anything we know. Decades ago, Carl Sagan himself speculated in print about microbial life drifting in exactly that cloud layer. It was a fringe thought then. It is a funded research question now. The debate since 2020 has been a proper scientific brawl, and the label on this claim must be written honestly. Contested. Reprocessing of the original data shrank the signal's strength. Other telescopes, observing in different ways at different times, found nothing. Skeptics proposed the team had misread ordinary sulfur dioxide. But the Discovery team's continued monitoring campaign with the James Clerk Maxwell telescope in Hawaii has kept recovering the phosphine line, deepening rather than retreating from the claim, and in 2024, a separate tentative detection added ammonia, another gas with no accepted non-biological source on Venus, to the mystery. What everyone agrees on is that the question is now answerable. NASA's Da Vinci mission and Europe's Envision orbiter head for Venus in the early 2030s, and privately funded probes aim to get there sooner, some designed specifically to fly through the clouds and test the chemistry directly. Within a decade or two, Venus will either be exonerated or become the biggest story in the history of science. The third world is not in our solar system at all, and it earns its place on this list as both a preview and a warning. K218b is a planet 124 light-years away, about 8.5 times Earth's mass, orbiting in the habitable zone of a small red star. Some models paint it as what astronomers call a Hycean world, a global ocean beneath a sky of hydrogen. In 2023, the James Webb Space Telescope read starlight filtering through its atmosphere and found methane and carbon dioxide, the first carbon chemistry ever confirmed in the air of a habitable zone planet. That much is solid. Alongside it came a whisper, a marginal hint of dimethyl sulfide, a gas which on Earth is produced almost entirely by ocean plankton, the molecule responsible for the smell of the sea. In April of 2025, the same team reported the hint again in new data, stronger, and the world's headlines announced the strongest sign of alien life yet found. Then the system worked. Independent teams reanalyzed the data within months, and the verdict, repeated several times over, was that the evidence does not hold. Treated with stricter statistics, the signal fades into the noise, and other unglamorous molecules fit the data as well as the exciting one. The honest label on K218b's dimethyl sulfide is not confirmed and likely not present at the levels claimed. That may sound like a defeat to end the item on, but hear what actually happened, because it is arguably the most hopeful thing on tonight's list so far. A telescope built by human beings measured individual molecules in the sky of a world so far away that its light left before most of the people listening to this were born. Rival teams then fought over the reading, in public, with mathematics, and the cautious side won the round. That is not failure. That is a working instrument attached to a working discipline of proof, aimed at the right question for the first time in history. Step back and see the three worlds together. A gas seeping seasonally from the ground of Mars that should not last. A gas drifting in the clouds of Venus that should not form. A gas argued in and out of the sky of a distant water world, at the very edge of our instrument's reach. Perhaps all three will dissolve into exotic geology and statistics, the way careful science often resolves its own excitements. But Lovelock's principle cuts both ways, and it is worth saying plainly. When the discovery of life beyond Earth finally comes, it will almost certainly come exactly like this. Not as a saucer or a voice, but as a stubborn wiggle in a spectrum, a gas that should not be there, a press conference hedged with the word potential, and years of argument. One of these three arguments may already be the real thing, working its slow way through review. The first contact, if it ever comes, will look less like a handshake and more like a decade of peer review. It is worth understanding why an atmosphere is such a powerful witness in the first place, because the logic is what makes gas detection the front line of the whole search. A single rock is a single sample from a single spot, and it can be a fluke, an oddity, a local accident. An atmosphere is planet-wide, and it is continuously renewed. Gases mix around a whole world in months or years, and reactive ones are constantly destroyed by sunlight, by chemistry, by contact with rock. So if a reactive gas is present in a steady amount, something must be replenishing it on a global scale, right now, against everything trying to remove it. That is a much harder thing to fake than a lucky mineral. It is why the discovery of life beyond Earth, when it comes, will most plausibly come from a spectrum rather than a specimen, from reading a whole planet's air across light years, rather than from touching a single stone. The three worlds in this item are the three places where that reading has already returned something that does not fit. The story of Venus carries a human turn that deserves telling, because it shows what it costs a scientist to make a claim like this. Jane Greaves did not go looking for life. She was studying the chemistry of planetary atmospheres, saw a faint dip in Venus's spectrum at the exact wavelength where phosphine absorbs, and spent months assuming she had made a mistake. She and her team ran the analysis again, checked it against a second telescope, and worked through every ordinary source of phosphine they could think of: volcanoes, lightning, sunlight-driven reactions, meteor dust, chemistry deep in the planet's crust. Every known process fell short by orders of magnitude. Only when they had exhausted the mundane explanations did they publish, and the moment they did, they became the target of exactly the scrutiny that good science demands and that no scientist enjoys. Their signal was reprocessed by others and shrank. Rival teams reported they could not see it. For a while, it looked as though the claim might simply evaporate. And then the Discovery team kept observing, and the line kept reappearing in their data, and the argument, rather than ending, deepened. That is not the arc of a debunked mistake. It is the arc of a genuine, unresolved anomaly, still standing years later, still contested, still waiting for a probe to fly through the clouds and settle it directly. The K218b episode is the one every viewer should hold on to, because it is the honest preview of how the real thing will feel, and it will not feel like certainty. A world 124 light-years away, a telescope reading the starlight that filters through its atmosphere as the planet crosses its star, and in that filtered light, the faint fingerprint of molecules. Methane, confirmed. Carbon dioxide, confirmed. And then the whisper of a gas that on Earth comes almost entirely from living oceans. The headlines wrote themselves. And then the correction came, not from cranks, but from the scientists' own colleagues, rerunning the numbers with stricter statistics and finding that the whisper faded into the noise, that other, duller molecules fit the data just as well. The claim did not survive. But notice what remained standing after it fell. We now live in a time when a human instrument can measure individual gases in the atmosphere of a planet so distant its light left before recorded history, and a global community of scientists can fight over the reading in public, in months, with mathematics, and the cautious side can win. The first real detection may already be somewhere in that pipeline, indistinguishable at first from a false alarm, working its slow way through exactly this gauntlet. When it clears, it will not arrive as a certainty. It will arrive as a claim that stopped being knocked down. It is worth stepping back to appreciate how the search for these gases will scale in the coming years, because the three worlds in this item are only the beginning of a much larger effort. The James Webb Space Telescope, already reading the atmospheres of the nearest and largest exoplanets, is the first instrument capable of this work at all, and it is straining at the very edge of its ability to do it. The generation of telescopes now being designed, enormous ground-based observatories with mirrors 30 meters across, and future space telescopes conceived specifically to image Earth-like planets directly, are being built with one headline goal above all others: to read the atmospheres of small rocky worlds in their stars' habitable zones and search them for the chemical signatures of life. The plan is not to check one or two planets, but to survey dozens, building a statistical picture of how often temperate worlds carry oxygen, methane, and the other telltale gases. If even a small fraction of them show atmospheres out of equilibrium, the conclusion will be almost impossible to avoid. This is the machinery being assembled right now, and the three arguments in this item, over Mars, over Venus, over K218b, are the first live tests of instruments and methods that will soon be aimed at hundreds of worlds. There is also a sobering discipline that this field has had to learn, and the phrase for it is the false positive. A gas that means life on Earth does not automatically mean life somewhere else, because an alien world may have chemistry we have not imagined, geology we have not sampled, conditions that manufacture a biology-associated molecule with no biology involved. Oxygen itself, long considered a gold standard sign of life, is now known to be producible without life under certain conditions, by sunlight splitting water vapor and the light hydrogen escaping to space, for instance. So the modern search does not hunt for a single magic molecule. It hunts for combinations, for oxygen together with methane, for a whole atmosphere that hangs in a disequilibrium no known geology can sustain, and even then it demands that every non-living explanation be chased down and eliminated first. This is why the K218b claim was met not with celebration, but with immediate, rigorous doubt from the very community that would most love it to be true. The discipline is not pessimism. It is the only way to make sure that when the announcement finally comes and holds, it holds for good. And it is worth holding all three of these worlds in mind together, because their differences are as instructive as their similarities. Mars is a cold, dry planet next door, its puzzle a gas that seeps and vanishes in defiance of its own chemistry. Venus is a scorched world wrapped in acid, its puzzle a gas high in temperate clouds where known chemistry cannot make it. K218b is a distant water world at the very limit of what our telescopes can read, its puzzle a molecule argued into and out of existence by rival teams. Three completely different environments, three completely different methods of detection, and yet the same underlying question in each. Is that gas the exhaust of something alive? That the question keeps arising, on worlds so unlike one another, is itself a kind of sign. Not proof, but a pattern, a reminder that the air of more than one world has begun to speak in a language we are only just learning to read. Gases, though, whisper. They demand patient instruments and statistical care, signals teased from noise over years. The next sign on our list did not whisper. It arrived as a scream from another galaxy, a flash lasting a fraction of a second that briefly outshone everything else in the radio sky. And when astronomers noticed that some of these flashes repeat, on schedules, from fixed points in the darkness, the word signal stopped being a metaphor. Number 4. The cosmic Morse code. The discovery that opens this item was made 6 years late by a student in a filing cabinet. In 2007, astronomer Duncan Lorimer of West Virginia University set his student David Narkovic a methodical task, combing through archived survey data from the Parkes Radio Telescope in Australia, tapes recorded back in 2001. Deep in that old data, Narkovic found something that should not have been possible. A single flash of radio energy, lasting less than 5 milliseconds, but so intense that it had briefly outshone every other radio source in the sky. In that fraction of a blink, whatever produced it released roughly as much energy as our sun pours out over several days. And it was not from the neighborhood. The flash carried an unmistakable stamp of distance. Its high frequencies arrived a fraction of a second before its low frequencies, smeared out by the thin fog of electrons that fills the space between galaxies, and the amount of smearing said the burst had traveled for billions of light-years. The event became known as the Lorimer burst, the first fast radio burst, and for years it was an orphan. Nothing like it appeared again, and a healthy fraction of the astronomy community quietly concluded it had been an instrument glitch or interference from something mundane. That suspicion seemed confirmed when similar signals turned up that were eventually traced to the observatory's own kitchen, a microwave oven opened mid-cycle. The real bursts, though, kept their distinctive stamp of distance, and slowly, as more telescopes caught more of them, the phenomenon graduated from possible glitch to confirmed mystery. The sky, it emerged, produces these millisecond screams constantly. Current estimates suggest that somewhere in the observable universe, a fast radio burst goes off thousands of times every day. The radio sky has been strobing like this forever. Until 2007, nobody had ever noticed. The instrument that industrialized the mystery is one of the strangest telescopes on Earth. CHIME, in the mountains of British Columbia, looks nothing like a dish. It is 4 fixed metal half-pipes, each the size of a snowboard half-pipe stretched 100 meters long, with no moving parts at all. It stares straight up and lets the sky rotate through its view, while a bank of computers processes the equivalent of a significant fraction of the world's internet traffic in real time, watching every direction at once for millisecond flashes. When CHIME switched on in 2018, humanity's total catalogue of fast radio bursts was a few dozen. CHIME found hundreds within its first year, and the catalogue now runs into the thousands. What was once a curiosity with a sample size of 1 became a population, with statistics, demographics, and most importantly, oddballs. The oddballs are why this item is on a list about company. Most fast radio bursts fire once and are never heard from again, consistent with cataclysms, deaths, collisions, final events. But a minority repeat. The first repeater, a burst originally caught at the Arecibo Observatory in 2012, was watched flashing again and again from exactly the same point on the sky, which ruled out any explanation involving destruction. Whatever makes it survives the making. In 2017, astronomers pinned that repeater's home address, a small dwarf galaxy some 3 billion light-years away, the first fast radio burst ever localized to its source. Then, in 2020, came the detail that pushed the mystery into genuinely uncomfortable territory. A repeater, catalogued from its discovery date in September 2018, turned out to burst on a schedule. 16.35 days, with a precision that has held for years. Roughly 4 days of activity, then silence, then activity again, like a lighthouse, with a very slow lamp. A second repeater later showed hints of a cycle of about 160 days. Order, rhythm, and timing, coming out of the depths of space, from sources that survive their own outbursts. You can hear why the phrase cosmic Morse code attached itself to these signals, and for a while, the artificial hypothesis was not confined to the Internet's imagination. In 2017, Harvard astrophysicists Avi Loeb and Manasvi Lingam published a calculation showing that the properties of fast radio bursts were consistent with something specific and technological. Planet-sized transmitters beaming power across space to push enormous light sails, with the bursts we detect being stray sweeps of those beams crossing Earth by accident. The paper was explicit that this was speculation, an exercise in checking whether physics forbids the idea. Physics, it turns out, does not forbid it. Let that be labeled exactly what it is: speculation, published by serious people, taken seriously as an exercise, and never supported by a single confirming observation since. It sits on the record as a mark of how strange these signals genuinely are. Sober professionals looked at the data and considered engineering among the possibilities. Then, on April 28, 2020, Nature staged a confession inside our own galaxy. That day, CHIME and a modest California instrument called STARE-2, built partly from cake pans as a low-budget experiment, both caught an enormously bright radio burst. This one carried no stamp of intergalactic distance. It came from inside the Milky Way, 30,000 light-years away, and its source was identified within hours, because the same object was simultaneously spitting X-rays at orbiting telescopes. The source was a magnetar, the most extreme kind of neutron star, a city-sized corpse of a dead sun, with a magnetic field roughly 1,000 trillion times stronger than Earth's, an object so magnetically violent that its crust cracks and quakes. Here, at last, was a fast radio burst with a face. A known object, in our own galaxy, of a known class, caught producing the phenomenon red-handed. If that magnetar had fired the same burst from another galaxy, it would have looked like a classic faint, fast radio burst. The case, in its broad outline, was cracked. Magnetars can do this. But listen to what the confession did not explain, because the remainder is where the mystery still lives. If magnetars are the engine, the clean 16-day schedule of that repeater needs a clock, and a lone spinning magnetar is a poor timekeeper on those scales. The leading guess is a binary system, a magnetar orbiting a companion star whose wind periodically blocks or frees the bursts, which would make the rhythm orbital, natural, and elegant. It remains a guess. Worse, one repeater was localized in 2021 to a globular cluster in the galaxy M81, a retirement home of ancient stars, precisely where young magnetars should not exist, because the star-forming furnaces that make them burned out billions of years ago. Something in that ancient cluster is firing fast radio bursts anyway. Perhaps a magnetar born through a rarer channel, the collapse of a white dwarf pushed over its weight limit. Perhaps something else. And no single model yet unifies the one-time bursts with the repeaters, the scheduled with the random. The engine room has been found. The engineering remains unread. So this item earns its place on the list not because fast radio bursts are aliens, but because of what they taught the search, and the lesson cuts in both directions at once. Direction 1. Nature can impersonate intention. Signals that repeat, keep schedules, survive their own emission, and concentrate unthinkable power into milliseconds can still come from magnetized dead stars, with no mind anywhere in the loop. Every future candidate signal, including the wow signal behind us on this list, and any signal yet to come, must climb over that hard-won standard of proof. The universe builds lighthouses. Finding a lighthouse is not finding a lighthouse keeper. Direction 2, and sit with this one. For the entire history of our species, until a student opened an old file in 2007, the radio sky was flashing thousands of times a day, and no human being knew. An entire channel of the universe's conversation, invisible for all of history, was switched on for us by one archived tape and one patient graduate student. The obvious question follows on its own. How many other channels are strobing right now, unread, waiting for their own filing cabinet moment? The sky does not owe us the courtesy of transmitting only on frequencies we have thought to monitor. The distance stamp these bursts carry is worth understanding, because it is the detail that rules out a local, mundane origin and forces the mystery out into the cosmos. Space between galaxies is not perfectly empty. It holds a thin haze of free electrons, and when a sharp pulse of radio energy passes through that haze, the different frequencies are slowed by different amounts. The high frequencies race ahead, the low frequencies lag behind, and by the time the pulse reaches Earth, a signal that left its source all at once arrives smeared across a fraction of a second, high notes first, low notes trailing. The amount of that smearing measures how much haze the pulse crossed, and therefore how far it traveled. For fast radio bursts, the smearing is enormous, far more than the entire Milky Way could produce. The number itself is the proof of distance, and it says these flashes are crossing billions of light-years of intergalactic space. Whatever makes them is not in our backyard, and it is releasing, in a thousandth of a second, energy on a scale that only the most violent objects in the universe can muster. The magnetar itself is worth dwelling on, because once you understand what one is, the fact that it can fire a fast radio burst stops sounding like a letdown and starts sounding like its own kind of marvel. A magnetar is what remains when a massive star dies and its core collapses into a ball of neutrons about 20 kilometers across, a city-sized object holding more mass than the Sun, so dense that a sugar cube of its material would weigh as much as a mountain. And a magnetar is the most magnetic object known to exist. Its magnetic field is 1,000 trillion times stronger than Earth's, strong enough that, at close range, it would scramble the molecules of your body, strong enough to warp the very structure of the atoms in its crust. When that field slips or the crust cracks, the object convulses, and it can release in a heartbeat an amount of energy that beggars comparison. That such an object can produce a millisecond radio flash bright enough to cross the universe is not a disappointment. It is a demonstration that nature, using nothing but a dead star and a monstrous magnetic field, can manufacture signals of a power and sharpness that look, at first glance, exactly like engineering. And that is the deep lesson this item leaves for the whole search, the reason it earns its place on a list about company, even though its answer, so far, is not company at all. Fast radio bursts are a lesson in humility, delivered twice over. The first humility is about impersonation. Before that magnetar confessed in 2020, the repeating bursts with their impossible power and their clockwork schedules were the single most engineered-looking phenomenon in the sky, and serious scientists put artificial transmitters on the list of candidates in print. Then nature revealed that a dead star could do it all, with no mind involved. Any real signal from a real civilization will have to clear a bar that these magnetars raised. The second humility is about blindness. The radio sky was strobing thousands of times a day for the entire span of human existence, and we did not know until 2007, until a graduate student happened to open an archived file. An entire loud, constant phenomenon, invisible to us purely because we had not built the right instrument and pointed it the right way. If we were deaf to that for all of history, the honest question is not whether we have heard everything. It is how much else is arriving right now, on channels we have not thought to monitor, in forms we have not learned to recognize, waiting for its own filing cabinet moment. There is a practical gift buried inside these bursts that deserves mention, because it turns even the unsolved mystery into a tool. As a fast radio burst crosses billions of light years, the smearing it picks up records everything its light passed through, all the thin, invisible gas strewn between the galaxies. For decades, astronomers had a problem. When they added up all the ordinary matter they could see in stars and galaxies, a large fraction of what should exist simply could not be found, hidden in wisps too faint to detect directly. Fast radio bursts weigh that missing matter automatically, because the amount of smearing on each burst is a running tally of all the gas along its path. In using these flashes to map the invisible skeleton of the cosmos, astronomers have begun locating the universe's missing ordinary matter, exactly where theory said it should be, but no telescope could confirm. A phenomenon we cannot fully explain has already become an instrument for solving a different problem entirely, which is a fair reminder that a mystery need not be understood to be useful. It is also worth appreciating just how far these signals travel, and therefore how far back in time we are seeing when we catch one. A burst, localized to a galaxy 3 billion light-years away, left its source 3 billion years ago, when the most complex life on Earth was still single cells in the sea. The flash raced across the widening universe for all that time, was stretched and reddened by the expansion of space itself, and finally ended its journey by landing on a fixed metal half-pipe in the mountains of British Columbia and registering as a millisecond blip in a bank of computers. Every fast radio burst is a message from the deep past, from an object that may no longer exist, delivered to a species that only learned to catch them a few years ago. The sky is full of these ancient deliveries, thousands a day, and for the whole span of human history we stood beneath them unaware, deaf by nothing more than the absence of the right receiver. That, more than any single burst, is the quiet lesson worth carrying forward from this item into the rest of the night. Fast radio bursts cross the universe at the speed of light, which is the speed limit for information, and everything on this list so far has obeyed it. Signals, spectra, the light of distant worlds, all of it messages, none of it matter. But in October of 2017, the universe delivered something in person. An object, solid and real, hundreds of meters long, fell in from the darkness between the stars, swung around our sun, and left. It was the first confirmed visitor from another star system in recorded history, and the more carefully astronomers measured it, the less it behaved like anything they had ever seen. Number 3. The visitor that did not belong. On the night of October 19, 2017, astronomer Robert Werrick was doing what he did most nights, reviewing images from the Pan-STARRS 1 telescope on the summit of Haleakala on the Hawaiian island of Maui. Pan-STARRS is a sentry. Its job is to photograph the sky over and over, hunting for anything that moves, mostly asteroids whose paths might someday cross Earth's. Moving objects are routine. What stopped Werrick that night was not that his new dot moved, but how. When he and his colleagues fit an orbit to it, the mathematics refused to close. Every asteroid and comet ever tracked, without exception, follows a closed loop around the Sun, an ellipse, bound by gravity like a ball swung on a string. This object's path was a hyperbola, an open curve. It was not orbiting the Sun. It was passing the Sun, moving at 26 kilometers per second more than escape velocity, a speed no slingshot from any planet in our solar system could account for. There was only one available conclusion, and it was historic. The object had fallen in from interstellar space. After centuries of astronomy, this was the first confirmed object from another star system ever observed inside our own. It was given the designation 1I, the first interstellar object, and a Hawaiian name, Oumuamua, which translates roughly as a messenger from afar, arriving first. The name would prove almost uncomfortably apt. And the circumstances of the discovery contained the first frustration, because Oumuamua was found on its way out. It had already made its closest approach to the Sun on September 9th, unseen, hidden in the Sun's glare, and had passed within about 24 million kilometers of Earth, roughly 60 times the distance to the Moon, 5 days before Werrick noticed it. By the time humanity knew its first interstellar visitor existed, the visitor was leaving, receding at a pace that gave the world's telescopes only a few frantic weeks before it faded beyond reach forever. Everything we will ever know about it was gathered in that closing window. What was gathered has not stopped bothering astronomers since. Begin with the shape. Oumuamua's brightness, watched hour by hour, swung by a factor of about 10, the object flashing bright and dimming dark on a cycle of roughly 8 hours. Brightness swings that extreme had never been recorded for any natural body. The straightforward reading is geometry. The object was tumbling end over end, and it was shaped like nothing in the catalogues, at least 6 times longer than it is wide by conservative estimates, perhaps 10 times by others. A few hundred meters long at most, shaped either like a cigar or, according to the models that best fit the light, like something even stranger, a flattened slab. A pancake. No asteroid or comet ever measured, out of millions, has proportions like that. Continue with the silence. A comet arriving from the cold between the stars should announce itself. Warmed by the sun, its ices should boil off into a glowing coma and a tail, the signature that makes comets comets. Telescopes searched Oumuamua for any trace of that breath, any halo of dust or gas, and found nothing. It was a bare point of light, reddish, the color of surfaces cooked for ages by cosmic radiation. The Spitzer Space Telescope, exquisitely sensitive to the heat glow of small bodies, looked for it and could not detect it at all, which set strict limits. The object was small and either unusually dark or unusually reflective, depending on the assumptions. A dead, dry, strangely shaped sliver of another solar system tumbling silently past ours. Odd, but perhaps just an unfamiliar kind of rock. Then came June of 2018, and the measurement that turned an oddity into a genuine anomaly. Marco Micheli of the European Space Agency and an international team had been tracking Oumuamua's fading trajectory with the Hubble Space Telescope and ground-based observatories, and the numbers would not fit gravity alone. The object was accelerating, gently and persistently, away from the Sun, as if something beyond gravity were pushing it. The effect was small, but it was unmistakable in the data, statistically overwhelming. Objects do not do that on their own. Comets do it all the time, because their venting gas acts as a weak rocket. But a comet's rocket comes with a comet's exhaust, the very coma and tail that every instrument had failed to find. Oumuamua had the push without the breath. It behaved like a comet that had forgotten to be visible. Astronomy then entered one of the most public hypothesis wars in its modern history, and the honest way to tell it is to lay the options on the table with their price tags attached. Option 1. Proposed in 2020, an iceberg of frozen hydrogen. Hydrogen ice vents invisibly, which would explain the push with no visible tail. The price is that hydrogen ice is so fragile that most calculations say a body made of it could not survive the long interstellar crossing. Option 2. From 2021, a shard of frozen nitrogen chipped off the surface of some other system's version of Pluto. Nitrogen venting is also nearly invisible, and the material matches the reflectivity. The price is bookkeeping. The galaxy would need to manufacture and shatter implausibly many Pluto-like worlds to make such shards common enough for one to be our very first visitor. Option 3. From 2023, currently the most favored family of models, the dark comet. In this picture, Oumuamua is a water-rich body whose long exposure to cosmic rays converted some of its ice into trapped molecular hydrogen. Sunlight warmed the body, the hydrogen leaked out and pushed, and pure hydrogen gas, carrying almost no dust, stays invisible to telescopes. It is a clever and economical idea. Its price is that it, too, describes a class of object nobody has ever confirmed at close range. And then there is the option that made this object a household name. In late 2018, Harvard astronomer Avi Loeb and his colleague Shmuel Bialy published a calculation showing that sunlight itself, the sheer pressure of photons, could produce exactly the observed acceleration, provided the object were extraordinarily thin, on the order of a millimeter thick across a span of tens of meters. There is a name for a millimeter-thin sheet pushed by light. It is a light sail, a technology human engineers are developing right now. Loeb argued, in journals and then in books, that the possibility that Oumuamua was artificial, a derelict sail or a deliberate probe from another civilization, deserved a place on the table alongside the exotic natural options. The overwhelming majority of astronomers disagree with him, and it is fair to say the mainstream position is that a natural explanation of some unfamiliar kind is far more likely. But notice the honest shape of the disagreement. Every option on the table, without exception, is something never observed before. A hydrogen iceberg has never been seen. A nitrogen shard of that kind has never been seen. A dark comet has never been confirmed. And a light sail has never been seen, except in our own laboratories, where we are building them. The debate was never between a mundane explanation and an exotic one. It was exotic all the way down. In 2022, formal analyses concluded the object was consistent with a natural body of an unknown class, which is the polite way of recording that the case was closed administratively, not intellectually. No photograph of Oumuamua exists beyond a shifting point of light. It left too quickly, and it is now beyond every telescope we own, outbound toward the constellation Pegasus, carrying its answer with it. For one moment, though, put yourself there, in September of 2017, at the closest any mind has come to it. You are standing on its surface as it rounds the sun. The ground under your boots is dark and reddish, cooked by 500 million years or more of cosmic rays, and it is turning, slowly, end over end. Every 8 hours, the whole sky wheels around you. The sun, huge and blinding at this distance, swings up over one short horizon, arcs overhead, and sets past the other, and in its place, the stars pour by, among them one soft blue point, Earth, unaware. There is no sound, no plume of gas hissing from vents. If the dark comet theorists are right, the push is happening under your feet even now, an exhalation of invisible hydrogen too thin to feel. If Loeb is right, the deck you stand on is thinner than a coin, and the light itself is the engine. Either way, The object does not care that it is being wondered about. It has been falling between the stars since before complex life existed on Earth, and our whole solar system, the only home we have ever known, is to it a brief brightening, one warm afternoon in a journey of epochs. What has happened since is the part of this story that trends quietly hopeful. Oumuamua turned out to be first, not unique. In August of 2019, a Crimean amateur astronomer named Gennady Borisov, using a telescope he built himself, discovered the second interstellar visitor, and the second one behaved perfectly. 2I Borisov was a comet, unambiguous and textbook, trailing gas and dust, its chemistry measurable and only mildly unusual. Borisov matters to this list for a precise reason. It is the control experiment. It proved that ordinary interstellar objects look ordinary, that our instruments detect their activity without difficulty, and therefore that Oumuamua's silence and strangeness were properties of the object, not failures of our equipment. Then, on July 1, 2025, the Atlas survey in Chile found the third visitor, 3I Atlas, another active comet, and this one arrived in time for the full power of modern instruments. The James Webb Space Telescope and the great observatories read its chemistry and found a body unlike any local comet, extravagantly rich in carbon dioxide, its water carrying a heavy hydrogen signature far stronger than Earth's oceans, its estimated age 10 to 12 billion years, quite possibly older than the Sun itself, a relic from an earlier generation of the galaxy's star systems, still traveling. The SETI Institute, being thorough, pointed the Allen telescope array at it across a broad band of frequencies and heard nothing artificial, exactly as expected for a comet, and exactly the kind of routine check that a mature search now performs. Here is the arithmetic that reframes everything this item has told you. 3 visitors in 8 years, found mostly by accident, by survey telescopes designed for other work, implies that interstellar objects are not rare pilgrims. They are constant traffic. Estimates now suggest that at any given moment, several such objects are passing through the solar system undetected, and that the galaxy is threaded with wandering debris from every star system it has ever built, planetary shrapnel and cometary cast-offs beyond counting, nature's own message in a bottle, exchanged between the stars for billions of years. The Vera Rubin Observatory, whose decade-long survey of the entire southern sky is now beginning, is expected to catch interstellar visitors by the dozen, catching them on the way in, with warning, rather than on the way out with regret. And mission designers, under the name Project Lyra and others, have already worked out how a prepared spacecraft could be launched to chase one down and photograph it up close. The next Oumuamua, and there will be a next one, may not get away clean. So file this item with precision. The first confirmed visitor from another star arrived, behaved in ways that still have no agreed explanation, and departed unphotographed. The second and third visitors were ordinary, which sharpens rather than softens the first one's strangeness. The traffic is continuous. The catalogue is about to grow enormously, and somewhere in that growing catalogue, the question left open in 2017 is waiting to be settled. Whatever Oumuamua was, the class of things it belongs to keeps arriving. We will meet more of them, and next time we will be looking. It is worth lingering on how narrow the window of observation truly was, because the shortness of that window is the tragedy at the heart of this item. From the moment of discovery on October 19th to the last usable measurement, astronomers had only a matter of weeks, and the object was fading fast the entire time, growing dimmer as it fled toward the outer solar system. Telescopes around the world dropped their scheduled programs and swung to it in a scramble, but even the mightiest instruments could pull only so much light from a few hundred-meter object already tens of millions of kilometers away and receding. There was no time to build a mission, no time to launch anything, no chance of a close look. Everything humanity will ever know about its first interstellar visitor was gathered in that brief, frantic autumn from a shifting point of light before it slipped beyond reach forever. The measurements we have, the tumbling brightness, the reddish color, the missing tail, the anomalous acceleration, are all we are ever going to get. The object took the rest of its answers with it. There is a piece of context that makes the anomalous acceleration even harder to shrug off, and it concerns just how carefully that measurement was made. This was not a rough estimate. Marco Micheli's team combined data from the Hubble Space Telescope with observations from the largest ground-based observatories, tracking the object's position over its final weeks with extraordinary precision. They accounted for every gravitational influence they could name: the sun, the planets, even the gentle pressure of sunlight on the object's surface. And after all of that, a residual push remained, small but statistically overwhelming, decreasing with distance from the sun in a way consistent with some kind of outgassing. The acceleration was not an artifact of sloppy tracking or a rounding error. It was a robust, carefully measured fact about the object's motion, and it is the single hardest thing to explain by any ordinary account, because ordinary comets that accelerate that way do it while wearing a visible tail, and this object wore nothing. The push was real, and the exhaust that should have accompanied it was, as far as every instrument could tell, simply not there. The hypothesis war is often told as a shouting match, but underneath the noise there was a genuine and productive scientific disagreement, and it is worth being fair to both sides of it. The mainstream position was never that the object was boring. It was that, faced with something genuinely unexplained, the responsible first move is to exhaust every natural possibility, however exotic, before reaching for the most extraordinary explanation of all. Hydrogen icebergs, nitrogen shards, dark comets venting invisible gas, each was proposed precisely because it could, in principle, produce a push without a visible tail, using only known physics and no intelligence anywhere. Avi Loeb's counter-argument was not that the natural explanations were impossible, but that they were each so unprecedented, so finely tuned, that the artificial explanation deserved to sit on the same table rather than being ruled out before consideration. He argued, in essence, for keeping an open mind about the one hypothesis that everyone's instincts wanted to dismiss first. The disagreement was real, it was public, and it was, in its way, the system working. A strange object arrived. The community argued fiercely about what it was, and in the end admitted, on the record, that it did not know. That admission, from a discipline that prizes certainty, is worth more than any of the individual theories. It is worth understanding why the Vera Rubin Observatory changes this story so completely, because it converts a matter of luck into a matter of routine. Oumuamua was found by accident, late, by a survey that was looking for something else, and it was found on its way out. Borisov was found by a dedicated amateur with a homemade instrument. 3I Atlas was caught by a survey built to spot dangerous asteroids. Every interstellar visitor so far has been a happy accident, noticed by machines pointed at other targets. The Rubin Observatory, now beginning a 10-year survey that will photograph the entire southern sky every few nights, changes the arithmetic entirely. It is expected to catch interstellar objects not by accident, but as a standing feature of its work, potentially many over the course of its survey, and crucially, to catch some of them on the way in, while they are still approaching, with weeks or months of warning, rather than a frantic few days of retreat. That warning is everything. It is the difference between watching a stranger's back as they leave and being ready at the door when they arrive. For the first time, the next Oumuamua may be seen coming. And that possibility opens a door that until recently belonged only to science fiction, the door of an actual mission. Engineers have already studied, under names like Project Lyra, how a spacecraft could be launched to chase down an interstellar visitor, using a slingshot around the sun to build the tremendous speed needed to catch an object that is only passing through. The mission is hard, because these objects move fast and give little warning, but it is not impossible, and with Rubin providing advance notice, the pieces begin to fit. Imagine it. A future interstellar visitor is spotted while still inbound. A prepared spacecraft, waiting on the ground or already in space, launches to intercept it, flies alongside, and does what no one could do for Oumuamua. It takes a photograph. It measures the shape directly, samples any gas, resolves the surface, and answers, in a matter of days, the questions that the first visitor carried away with it forever. We may not have to keep wondering about the class of objects Oumuamua belonged to. We may, within a decade or two, simply fly out and look one in the face. The mystery of the first visitor is not a permanent condition. It is a challenge we are actively preparing to meet. Everything on this list so far has kept a respectful distance, light years away, or millions of kilometers, or safely archived on paper. The next item closes that distance completely. These records were made inside Earth's own sky, over our own oceans, by military sensors and trained air crews, and they come with a detail no other item on this list can offer. The government of the most heavily instrumented nation on Earth has examined them, under oath, and its official conclusion is 2 words long: unresolved and unexplained. Number 2. The videos. The Pentagon confirmed. This item must be handled differently from every other item on the list, so let the ground rules come first. Nothing in the next several minutes is evidence of extraterrestrial visitors, and no official body has ever claimed otherwise. What this item documents is something more careful and, in its own way, more remarkable. Over the past 2 decades, the question of unidentified objects in the sky migrated from the tabloid rack into the congressional record, the Pentagon's org chart, and NASA's research portfolio, and it made that journey because trained military crews, backed by some of the most sophisticated sensors on Earth, kept recording things their own institutions could not explain. The sign here is not a saucer. The sign is a government, under oath, saying the words we do not know. The story's foundation is 4 minutes over the Pacific. On November 14, 2004, about 100 miles southwest of San Diego, the aircraft carrier Nimitz and its strike group were running training exercises. For nearly 2 weeks beforehand, the cruiser Princeton, carrying one of the most advanced radar systems in the fleet, had been tracking intermittent objects that behaved like errors. They appeared at 80,000 feet, higher than any conventional aircraft operates, then dropped toward the sea in moments, then hovered. Operators recalibrated the system, expecting to erase a glitch. The tracks stayed. That morning, the Princeton vectored 2 F-18 crews, including Commander David Fravor, commander of an elite fighter squadron, and Lieutenant Commander Alex Dietrich, to intercept one. What the 4 aviators in those 2 jets reported, consistently, across 20 years of retellings, under oath before Congress, is this. Below them, the ocean surface was disturbed, churning in a frothing patch, as if something sat just beneath it. Above the disturbance, holding position, was a white object shaped, in Fravor's now famous description, like a tic-tac, roughly 40 feet long, the size of his own aircraft, with no wings, no rotors, no visible engines, no exhaust, and no markings. As Fravor spiraled down toward it, the object began to mirror him, rising as he descended, the 2 aircraft tracing opposite arcs of the same circle. Then, as he cut across the circle toward it, the object accelerated and was gone, not fast the way jets are fast, but gone in under a second, in the manner of something that does not share an aircraft's relationship with momentum. Moments later, the Princeton called the second crew with an update that still hangs over this entire subject. The object had reappeared on radar at the flight's pre-briefed rendezvous point, 60 miles away. As if, the aviators have noted since, it knew where they were going next. A second flight launched later that day recorded the encounter's only sensor artifact, the infrared video later labeled FLIR 1, a grainy monochrome clip in which a small blob of heat slides out of the targeting frame. In January 2015, off the American East Coast, air crews from the carrier Theodore Roosevelt recorded 2 more clips with upgraded targeting pods. One, called Gimbal, shows an object apparently rotating in place against the wind while pilots exclaim on the intercom. The other, called Go Fast, shows a small object seemingly racing across the sea while the crew whoops with excitement. 3 short videos, none of them spectacular to the untrained eye, all of them destined to become the most scrutinized military footage of the century. Because here is what happened next, and the sequence of institutional dominoes is the real content of this item. In December 2017, the New York Times revealed that the Pentagon had been quietly running a program to study such reports, funded at $22 million, and it published the 3 videos. For 2.5 years, the clips circulated in a limbo of leaks. Then, on April 27, 2020, the Department of Defense did something without precedent. It formally released the 3 videos and confirmed on the record that they were authentic Navy recordings of phenomena the department categorized as unidentified. The word from the building that names everything was, officially, "We cannot name this." The dominoes kept falling. In June 2021, the Office of the Director of National Intelligence delivered a mandated report to Congress, a 9-page preliminary assessment that became a landmark not for what it claimed, but for what it counted. Of 144 reports from military sources between 2004 and 2021, the intelligence community could explain exactly one, a large deflating balloon. 143 remained uncategorized. 18 of them, the report noted in its most quoted passage, appeared to demonstrate unusual flight characteristics, movement patterns or capabilities the analysts could not readily account for, with the careful caveat that sensor errors, spoofing, and misperception could not be excluded. In May 2022, Congress held its first public hearing on the subject in over 50 years. In July 2022, the Pentagon established a permanent office with one of the great bureaucratic names, the All-Domain Anomaly Resolution Office, ARO, charged with collecting and resolving reports across every service. And in 2023, NASA convened an independent study team, 16 scientists chaired by astrophysicist David Spergel, whose conclusions were a model of the register this whole list aims for. No evidence that any UAP has an extraterrestrial origin, the panel found, paired with a pointed complaint that the data is poor, unstandardized, and stigmatized, and a recommendation that the subject deserves rigorous scientific attention rather than ridicule. NASA appointed a director of UAP research. The stigma, the panel noted, had itself become an obstacle to answering the question. Every honest telling of this story must now give the skeptics the floor, because their case is strong and specific. Go Fast, analyzed frame by frame using the numbers displayed on the targeting pod itself, is almost certainly an illusion of speed. The trigonometry suggests an object moving at modest wind drift velocity, high above the water, its apparent racing produced by parallax from a fast-moving camera platform. It may well be a balloon or a bird. Gimbal's dramatic rotation matches the known mechanical behavior of the camera pod itself. The targeting system's gimbal mechanism rotates while tracking, and glare from a heat source, such as a distant jet's exhaust, rotates with the optics rather than the object. What looks like a saucer tumbling against the wind may be a smear of infrared glare pirouetting inside the camera. Even FLIR 1 shows, on its face, an unremarkable blob whose sudden slide off screen can be read as the camera losing lock rather than the object darting away. These analyses come largely from independent researchers, and ARO's own resolved caseload points in the same direction. The office reports that with better data, most cases collapse into balloons, drones, satellites, aircraft, birds, and sensor artifacts. In its major 2024 historical review, ARO stated it found no evidence that any investigated case represented alien technology, and no evidence that any secret program has recovered off-world materials, directly contradicting the most sensational whistleblower claims aired before Congress the previous year. And yet, when every one of those deflations is granted in full, a residue remains, and the residue is official. The Nimitz encounter itself has never been explained, and it never rested on video. It rests on 4 aviators' eyes, a cruiser's radar tracks, and that rendezvous point detail, a chain of trained human testimony and independent sensors that no parallax argument touches. The intelligence community's own count began at one explained case out of 144. ARO's own reporting acknowledges that a stubborn fraction of cases, roughly 2 in 5 by recent accounting, remain unresolved after analysis, some involving multiple sensors at once. Hearings with military witnesses have continued year after year through 2025, with new footage shown and new testimony taken. In 2026, the American government began publicly releasing its historical files on the subject. Decades of reports, photographs, and investigations, an archival opening without precedent in this field. None of it proves visitors. All of it proves that the most sensor-saturated military on Earth keeps recording events in its own training ranges that survive its own review process unexplained, and that the era of pretending otherwise is over. Weigh this item on the same scale as the rest of the list, and its true shape appears. The universe-facing items gave us worlds by the hundreds of millions, and chemistry mid-argument on 3 planets. This item is different in kind. It is the only one where the unexplained thing was recorded inside our own atmosphere, at close range, by instruments built to track fast-moving machines, and where the institution that owns the instruments has said, formally and repeatedly, that it cannot resolve what they recorded. The mundane endings remain the most likely endings: foreign drones, sensor ghosts, secret programs seen from the wrong side. But 2 decorated aviators have now spent 2 decades answering questions about the strangest 4 minutes of their careers, telling the same story to journalists, admirals, and Congress without embellishment or retreat, and the official answer to what they saw over the Pacific that morning is today what it was in 2004. Unidentified. In a subject drowning in certainty from both directions, that stubborn institutional we do not know may be the most honest data point there is. It is worth understanding why the language shift matters, because it marks a genuine change in how the subject is treated, not merely a change in fashion. For most of the 20th century, the acronym was UFO, Unidentified Flying Object, 3 letters so freighted with tabloid associations that no serious officer wanted them near a career file. The stigma was itself a data problem. Pilots who saw something strange learned not to report it, because reporting it invited ridicule and grounding. The new term, unidentified anomalous phenomena, was chosen deliberately to strip away the flying saucer connotations and to make room for reporting without career suicide. That is the real content of the institutional change. Not a confession that visitors are real, but the construction of a channel through which trained observers can report anomalies and have them logged, analyzed, and in most cases, resolved. The value of that channel is precisely that it produces resolutions, that it converts a mystified pilot's account into an identified balloon or drone most of the time, and flags the residue that resists explanation for further study. A subject that was once pure folklore now has a reporting form, a database, and an office with a budget. That is what it looks like when a question moves from the margins into the machinery of science and government. The residue itself deserves a careful, honest characterization, because it is neither nothing nor proof. When RO and the intelligence community work through a case with good data, most collapse into ordinary explanations, and the office has been clear about this. Camera artifacts, atmospheric effects, distant aircraft, balloons, the proliferation of drones, birds, even reflections and lens flares account for the large majority. But a stubborn fraction survives that analysis, and survives it not because the objects performed miracles, but because the data is simply too thin to resolve. A fleeting sensor return, a witness account with no corroborating instrument, a track that cannot be reconstructed. Some of the surviving cases, though, are more troubling than mere thin data, because they involve multiple sensors at once, radar and infrared and human eyes agreeing on something that behaved oddly. The Nimitz encounter is the archetype. It has never rested on a single blurry video. It rests on a cruiser's advanced radar, on the eyes of 4 trained aviators, and on that detail of the object reappearing at the pre-briefed rendezvous point 60 miles away, a chain of independent observations that the parallax and glare arguments, powerful as they are against the videos, do not touch. That case remains open, and its openness is officially acknowledged. None of this should be oversold, and the discipline of this list requires saying clearly what the honest ceiling on this item is. There is no verified physical evidence, no recovered craft, no material that laboratories have confirmed came from beyond Earth, and the responsible agencies have said so directly, contradicting the more sensational claims made under oath by some witnesses. The most probable explanations for the unresolved residue remain earthly, foreign surveillance technology, classified programs seen from the outside, sensors deceived in ways not yet reconstructed. What makes this item belong on the list is not that any of it proves company. It is the narrower, sturdier fact that the most heavily instrumented military on Earth records events in its own airspace that survive its own review unexplained, and that its government now says so on the record, under oath, in hearing after hearing, rather than pretending the events did not happen. In a subject where certainty is sold cheaply by believers and debunkers alike, that institutional refusal to claim more than the evidence supports, that plain we do not know, is itself the most valuable thing in the file. It is worth being precise about what the pilot's training adds to their testimony, because it is the reason these accounts carry weight that a random eyewitness account would not. Fighter aviators are, by profession, expert observers of objects moving through the air at high speed. Judging distance, closing rate, altitude, and the behavior of aircraft is not a hobby for them, but the daily discipline on which their lives depend. When a pilot like David Fravor says an object descended from tens of thousands of feet to just above the water in a moment, or accelerated out of a turn faster than any airframe he knows, he is not a startled bystander guessing at lights in the sky. He is a trained professional reporting, in technical terms, that something violated the envelope of performance he has spent a career learning. That does not make him infallible. Trained observers can still be fooled by unusual geometry, by glare, by the genuine difficulty of judging an unfamiliar object with no known size. But it does mean their reports cannot be waved away as mere excitement or inexperience, and it is precisely why the institutions eventually took them seriously enough to build an office around them. There is a broader point worth drawing out about why this subject sits so awkwardly between science and secrecy, because that awkwardness is much of what keeps it unresolved. The best sensors that record these events belong to the military, and the military's instinct is to classify, not to publish. Radar capabilities, sensor resolutions, the exact performance of a targeting pod, all of it is guarded, which means the very data that scientists would need to resolve a case is often the data that national security keeps locked away. The NASA study panel pointed directly at this tension. Good science needs open, calibrated, shareable data, and this field has been starved of exactly that, its best evidence trapped behind clearances and its reporting deformed by decades of stigma. The reforms of recent years, the reporting channels, the dedicated office, the push to declassify historical files, are all attempts to pry the data loose and subject it to ordinary science. Whether they succeed is still an open question. But the direction of travel is unmistakable, from ridicule and secrecy toward daylight and analysis, and that shift alone, whatever it eventually reveals, is a genuine change in how seriously the question is being asked. And with that, the outward-facing evidence rests. 10 items promised, 9 delivered, and notice what the 9 have in common. Every one of them points away from here, out toward other stars, other oceans, other sky. The last item on this list does not point that way. It points at the floor under you, at the air you are breathing right now, at the one world in the universe where the question of life has already been answered. Because the single most obvious sign that we are not alone has never been hiding in the data of some distant telescope. It has been in plain sight for 2 billion years. It is us. Number 1. The sign in plain sight. For 9 items, we have searched outward. We counted the worlds, tasted the oceans next door, held a rock from Mars, argued over gases and signals, chased a visitor from another star, and read the government's own admission that it cannot name everything in its sky. Every one of those signs pointed away from here. And every one of them, in the end, was a maybe. A promising world with its atmosphere still pending. A signal heard once and never again. A leopard-spotted rock sealed in a tube, waiting for a ride. The honest verdict on items 10 through 2 is that they are, collectively, a mountain of suggestive, unconfirmed evidence. The item at number 1 is not a maybe. It is the one confirmed case of life in the entire universe, the single data point every other item on this list is implicitly compared against, and it has been sitting beneath your feet, above your head, and inside your lungs for your entire life. The most obvious sign that we are not alone is that we are here at all. Earth is the proof of concept. And the reason it belongs at the top of this list, rather than being dismissed as a trick of wording, is that Earth does not merely contain life. Earth broadcasts it, legibly, across interstellar distances, and it has been doing so, without pause, for roughly 2 billion years. If anyone has been watching, we were never hidden. This final item assembles the proof in 4 parts. The first part is an experiment we performed on ourselves, and almost no one has heard of it. In December of 1990, NASA's Galileo spacecraft was on its long, looping route to Jupiter, and its path brought it swinging back past Earth for a gravitational boost. Carl Sagan saw an opportunity no one had ever taken. Here was a sophisticated alien-hunting spacecraft, loaded with instruments, about to fly past a planet that we knew, for absolute certain, was teeming with life. So Sagan convinced NASA to turn Galileo's instruments on Earth and run a controlled test of the only kind ever possible. Can a passing spacecraft detect life on a world already known to have it? Could we, in other words, even recognize ourselves? The results, published in 1993, are the quiet backbone of this entire item, because they defined what an obvious sign actually is. Galileo found 3 things. First, an atmosphere wildly out of chemical balance, oxygen and methane coexisting in defiance of chemistry, exactly the disequilibrium that Lovelock said only life could sustain. Second, a strange, strong absorption of red light blanketing the continents, a feature matching no rock or mineral, which we know to be the signature of chlorophyll, the collective glow of every forest and grassland, what scientists call the red edge of vegetation. And third, the one sign that required not just life, but minds. Narrowband radio emissions, pulsed and modulated, rising from the surface, carrying the unmistakable stamp of technology. Sagan's team concluded, with deliberate understatement, that the measurements were strongly suggestive of life and of intelligence on Earth. We pointed our best instrument at ourselves, and sure enough, we showed up. Every search on this entire list, the hunt for unstable gases on Mars and Venus and K218b, the hunt for narrowband signals from Sagittarius, uses precisely the checklist Galileo confirmed by looking in the mirror. We are not guessing what the fingerprint of a living world looks like. We photographed our own. Recall now the checklist from the very first item on this countdown, all those hours ago. Water in liquid form. Gases in the air that should not last. A signal with order in it. That was the searcher's checklist, the 3 things astronomers look for when they scan a distant world. Here, at number 1, is where the checklist turns around and reveals what it always was. It is not a list of things to look for out there. It is a portrait of Earth, drawn from space, in 1990. The checklist was a self-portrait all along. When we search the galaxy for water, restless chemistry, and ordered signal, we are searching for other planets that resemble the only one we have ever confirmed. We are looking for more of us. The second part is the broadcast, and it is the fact that should genuinely rearrange how you think about hiding and being found. There is a common and comforting assumption that Earth has only recently become detectable, that our radio and television leakage, about a century and a couple of decades deep now, is the first whisper we have sent into the dark. That assumption is wrong by a factor of 10 million. Around 2.4 billion years ago, Earth's atmosphere filled with oxygen, in the great transformation geologists call the Great Oxidation Event, the exhaust of the first photosynthetic life. From that moment forward, for 2 billion years and counting, Earth's air has carried that same screaming chemical disequilibrium that Galileo detected, oxygen and methane together, readable by exactly the method the James Webb Space Telescope now trains on TRAPPIST-1 and K218b. Any civilization within hundreds of light-years, holding a telescope even slightly better than the ones we are building this decade, could have read Earth as inhabited before there were animals here, before there were plants on land, before there was anything on this planet more complicated than pond scum. Our radio bubble, the sphere of our accidental transmissions, is a little over a century wide and already encloses something like 15,000 star systems, and it grows by nearly 2 light-years every year. But the radio is the new part, the loud and recent shout. The air gave us away 2 billion years earlier. If anyone nearby has ever looked with care, Earth was flagged, catalogued, and filed as a living world an eternity ago. We have also, once, shouted on purpose, and it recalls the wow signal from earlier on this list in a way worth pausing on. In 1974, astronomers used the Great Arecibo dish in Puerto Rico to beam a deliberate 3-minute message toward a cluster of stars called M13, a coded picture of our chemistry, our biology, and ourselves. It is traveling still, and will not arrive for about 25,000 years. Remember the wow signal, 72 seconds of steady tone that swept a telescope in Ohio and vanished. And remember what we said 72 seconds really was. The width of the keyhole, the size of the fragment one observer catches as geometry drags the beam across the sky. Now, turn it around. Our own leakage, our radio and radar and the Arecibo shout, is crossing other skies at this moment, and to any distant listener, it will arrive exactly as our wow signal arrived to us. A fragment. A tone that rises, holds, and fades as their world turns. Something heard once, argued over, filed as a maybe. We have spent this whole list being the puzzled receiver. We have been the mysterious transmitter the entire time. The third part is the timing, and it speaks to whether life is a miracle or a habit. Earth formed about 4.5 billion years ago, and for its first 500 million years, it was a hell of bombardment, repeatedly sterilized by impacts large enough to boil the oceans. The window for life to begin did not truly open until roughly 4 billion years ago. And life, on the evidence, walked through that window almost immediately. There are confirmed fossils of microbial mats, stromatolites, in Australian rock 3.5 billion years old. There are chemical traces suggestive of life in Greenland formations reaching back 3.7 billion years, and contested hints in mineral grains as old as 4.1 billion. Which means that on the one and only world where we can check, life appeared essentially the moment conditions allowed, not after a long improbable wait, but promptly, eagerly, like water finding the shape of its container. Now, honesty demands the caveat, and it is a real one. A sample size of 1 cannot prove the odds. It is logically possible that Earth is a freak, that abiogenesis is a once-in-a-universe fluke, and we are simply the ones who exist to notice, because only a winning ticket can ask about the lottery. That argument is valid and cannot be dismissed. But it must be set beside the one piece of data we actually possess. And that data point does not read reluctant. On the only trial we can examine, life did not behave like a miracle waiting billions of years for its chance. It behaved like chemistry doing what chemistry does, the moment it was allowed. The fourth part is the corollary, and it must be delivered in the calm register this channel keeps even for its largest thoughts. Assemble what this list has laid down. Hundreds of millions of potentially habitable worlds in this galaxy alone. Oceans by the handful in our own small solar system, most owing nothing to the sun's warmth. Chemistry mid-argument on 3 separate worlds. A confirmed proof of concept, us, where life started as early as it possibly could. Now add the arithmetic of time. The galaxy is roughly 13 billion years old. Our technological age is about 120 years old. If other technological civilizations exist, the overwhelming likelihood, given those numbers, is that they are not our contemporaries in any meaningful sense. They are older. Not by centuries, but very plausibly by millions of years, with our entire recorded history a rounding error against their age. And that gap is where a labeled idea enters, the one this list has been quietly walking toward. In 1973, the radio astronomer John Ball proposed what he called the zoo hypothesis. Perhaps, he suggested, the reason a galaxy that should be full of company stays silent is not that the company is absent, but that mature civilizations observe without touching, the way a park ranger watches a valley without introducing themselves to the deer. Label it clearly, because this list keeps its promises. The zoo hypothesis is speculation, and it carries a known and fatal weakness. It cannot be tested, and an idea that forbids its own disproof is not science. It is a possibility. But it is a possibility consistent with every single observation on this list, including the silence, and including, if you let yourself wonder, the 2 decades of unresolved objects in our own sky from the previous item. If the arithmetic of time is right, then the question was never whether we could find them. If they are out there, they found us first, and long ago, because we have been the obvious sign in someone else's sky since before we were human. Sit with that reversal for a moment, because it is the emotional center of this entire list. We picture ourselves as the searchers, sweeping the dark with our telescopes, hoping for a sign. But Earth has been a lighthouse for 2 billion years. Every generation of life that has ever lived on this planet, every trilobite and fern and dinosaur and ancestor, lived under a sky into which their own world was steadily broadcasting the fact of their existence, in a language of chemistry any competent astronomer in the neighborhood could read. The searchlight was never only ours. We have been visible for the whole of our existence, and for 2 billion years before it. If there has been anyone within a few hundred light-years capable of looking, we have never once been hidden. There is a detail in the Galileo experiment that deserves its own moment, because it captures how strange and how honest the whole exercise was. When Sagan's team analyzed the radio data, they found that the narrowband signals from Earth's surface were not natural. Natural radio sources, stars, planets, the galaxy itself, spread their emissions smoothly across the spectrum. What Galileo detected instead was radio energy concentrated into narrow channels and modulated, its amplitude varying in structured ways. That modulation, the team wrote, was the only one of the three signs that could not be explained by any known natural process. The unstable atmosphere might, conceivably, be mimicked by exotic chemistry. The red edge might, with imagination, be argued as some strange mineral, but the modulated narrowband radio could only mean technology. In other words, the single most decisive proof of intelligence that Galileo found on Earth is exactly the kind of signal that the WOW search, and every radio search since, has been straining to hear from someone else. We already know it works because we detected our own. The method is not theoretical. It caught us. It is worth being precise about the 2 billion year figure, because the instinct is to assume our visibility is a recent and fragile thing, and that instinct is badly wrong. Break the timeline into its two very different halves. The radio half is young, a little over a century, a thin shell of accidental broadcasts expanding outward at the speed of light, and it is not even growing as loudly as it once did, because efficient digital transmission leaks less into space than the blaring analog signals of the 20th century. If our detectability rested on radio alone, it would be a faint and recent thing, easy to miss. But the chemical half is ancient and immense. Since the Great Oxidation Event, since oxygen first flooded the air more than 2 billion years ago, Earth's atmosphere has carried the loud, continuous chemical signature of life, the disequilibrium that only a living biosphere sustains. That signal does not travel outward as a shell. It is simply written into the light of our planet, readable by anyone who can catch Earth crossing the face of the sun and split that light into its colors, exactly as we now do for distant worlds. For 2 billion years, any sufficiently advanced astronomer within a few hundred light-years, looking at the right moment, would have read Earth as unmistakably, chemically alive. We were not recently switched on. We have been the brightest biological beacon in this corner of the galaxy since long before there were eyes on this planet to wonder who might be watching. And this is where the reversal reaches its full depth, if you let it settle. We have spent this entire list cast as the seekers, the ones sweeping the dark, straining at the edge of detection, hoping. But turn the Galileo experiment around one final time. It proves that a passing observer can read a living world because we did it to ourselves. It proves that the fingerprint of life is legible across space because we lifted our own. And it proves, by the simple arithmetic of 2 billion years against 100, that if anyone with our own decade's technology has ever passed within a few hundred light-years and bothered to look, they did not need us to shout. Our air confessed for us, continuously, across an eternity, in a language any competent astronomer would read on the first night. The searchlight we imagine ourselves shining into the dark has been pointed back at us the whole time, and we have been standing in it, lit up, for the entire history of our kind, and for the long ages of simpler life before us. It is worth pausing on the honest weakness of the zoo hypothesis, because this list has promised to label its speculation, and the labeling itself is instructive. The idea that advanced civilizations watch without touching cannot be tested, and an idea that forbids its own disproof is, strictly speaking, not science. It explains the silence, but it would explain any silence, and a theory that predicts everything predicts nothing. So it must be held lightly, as a possibility rather than a finding. And yet there is something worth noticing about it, which is that it fits. It is consistent with the abundance of worlds, with the ease and early arrival of life on the one planet we can check, with the enormous head start that time would give any neighbors, and with the great and puzzling quiet that a galaxy so apparently fertile has kept. It does not prove company. Nothing on this list proves company. But it is one of the few pictures in which all the pieces of the evidence, the crowded sky and the empty airwaves, sit together without contradiction, and that is why serious people keep it on the table, clearly marked as the speculation it is. There is a final way to hold all of this that neither overclaims nor despairs, and it is the register this channel prefers. We do not know that we are not alone. That sentence must be said plainly, because everything on this list, taken honestly, is evidence and not proof, suggestion and not confirmation. But we do know something that our ancestors did not, and it is not small. We know the worlds are there, by the hundreds of millions. We know the ingredients are common, sprayed into space by moons in our own solar system. We know that on the single world we can examine from the inside, life appeared early, spread widely, and has been broadcasting its presence for 2 billion years. And we know that we, the searchers, are ourselves the one confirmed instance of the thing we are searching for, which means the phenomenon is real, has happened at least once, and left, in us, a working example of what a living world looks like from the outside. The question is no longer whether life is possible. We are the proof that it is. The only open question is how lonely that proof turns out to be. So let this list close where it has quietly been heading the whole way down. Return to the checklist one final time. Water. Restless air. An ordered signal. Every item on tonight's countdown was a world, or a signal, or an object that matched one or two lines of that checklist and left us wondering about the rest. A promising planet with water but unknown air. A signal with order but no sender. A chemistry mid-argument. Each of them a partial match, a fragment of the pattern. And Earth is the completed entry. The one place where every line of the checklist is not a hope but a measurement. Liquid water, confirmed. Restless chemistry, confirmed. An ordered signal, confirmed, and we are the ones sending it. Earth is the universe's single proof that matter, given time and warmth and an ocean, can wake up, look around, and ask whether it is alone. And a universe that managed that trick once, this early, this loudly, in a galaxy holding hundreds of millions of chances and an ocean of time to try them in, is not a universe that feels built for a single occurrence. We have not yet met the others. We may be waiting a very long time, and we may be waiting inside a silence we do not yet understand. But the most obvious sign that we are not alone was never going to arrive from the depths of Sagittarius or the clouds of Venus. It has been here the entire time, in the oxygen entering your lungs as you rest, refreshing a signal that has been legible from other stars since before your kind of creature existed. You are made of the only confirmed answer to the largest question there is. You are the sign. Let that keep you company tonight, gently and without fear. Sleep well and good night.